Hello there, and welcome to our journey through the quiet corners of space. Tonight, we will explore something wonderful, something vast, and something that surrounds us every moment of our lives. We are going to discover the objects that could wipe our planet from the history of the universe. Before we begin, I would love to know where you are listening from tonight. Perhaps you are in a quiet room, maybe lying back with your eyes closed. No matter where you are, we share this moment together, floating on our small planet through the vastness of space. If you find these kinds of quiet explorations interesting, I would be grateful if you could subscribe or like this program. It helps this gentle signal reach other curious minds who might enjoy these peaceful journeys through science. Take a moment now to settle in. Let your thoughts slow down to match the patient rhythm of deep and dangerous universe secrets. Deep within the cosmic archives of our Earth lies evidence of the most catastrophic collision in our planet's history. 4.5 billion years ago, when our solar system was still a violent nursery of forming worlds, a Mars sized wanderer named Theia approached on a collision course with the young Earth. This encounter would unleash forces so tremendous that they nearly obliterated our world entirely. The early Earth existed in a realm far different from today's tranquil blue marble. Our planet was a molten hellscape, constantly bombarded by cosmic debris in what scientists call the chaotic late accretion period. Temperatures soared beyond the melting point of rock. The atmosphere consisted of vaporized silicates and metals, creating a suffocating blanket of superheated gas around our forming world. Into this primordial violence came Theia, a planetary embryo, roughly 10% the mass of modern Earth. Scientists believe this cosmic wanderer originated at one of the gravitational sweet spots in Earth's orbit, known as Lagrange points, where smaller bodies can hide in gravitational stability for millions of years. But gravitational perturbations from Jupiter and Venus eventually nudged Theia from its safe harbor, setting it on a fateful trajectory toward our world. Computer simulations reveal the shocking details of this ancient apocalypse. They were approached at a velocity of more than 9 kilometers per second, striking Earth at approximately a 45-degree angle. The impact released energy equivalent to 150 times the force that would later extinguish the dinosaurs. In cosmic terms, this represented a moderate velocity collision, yet its consequences were anything but. The collision itself lasted mere hours, but its effects reshaped our planet permanently. The Theia's iron-rich core plunged deep into Earth's molten interior, merging with our planet's growing heart. Meanwhile, the mantles of both worlds exploded outward in a spectacular fireworks display of vaporized rock and metal. Temperatures reached 25,000 degrees Fahrenheit, hot enough to vaporize virtually any known material. Within this cosmic maelstrom, something extraordinary occurred. The impact ejected massive amounts of debris into orbit around the devastated Earth. This ring of molten material, heated beyond imagination, began a remarkable transformation. Gravity slowly gathered these scattered fragments, and within as little as 40 years, they coalesced into a new celestial body, our moon. Research suggests this formation process happened with startling rapidity. Recent high-resolution simulations indicate that the moon may have formed not over months or years, but in a matter of hours following the impact. Material from both Earth and Theia was launched directly into orbit, where it immediately began the process of gravitational assembly that created our lunar companion. The evidence for this cosmic catastrophe remains hidden in plain sight. Lunar samples returned by Apollo astronauts contain isotopic signatures nearly identical to Earth's rocks, suggesting extensive mixing between the two colliding worlds. The moon's unusual composition supports this violent origin story. It contains far less iron than Earth because most of Thea's metallic core remained embedded in our planet. Additionally, the moon shows a severe depletion of volatile elements like potassium and zinc, which would have been vaporized and lost during the high temperature formation process. Scientists have discovered other intriguing clues buried deep within our planet. Seismic studies reveal two massive blob like structures in Earth's lower mantle, each roughly twice the mass of the moon itself. These mysterious formations, known as large, low velocity provinces, may represent the preserved remnants of Thea's mantle, dense fragments that survived the collision and settled into our planet's depths billions of years ago. The chlorine isotope ratios in lunar rocks provide additional compelling evidence. Earth retains primarily light chlorine isotopes, while moon rocks show an abundance of heavier chlorine variants. This suggests that during the aftermath of the collision, Earth's stronger gravity selectively captured the lighter elements, leaving the forming moon enriched in the heavier isotopes. Perhaps most remarkably, this cosmic catastrophe may have been essential for life's eventual emergence on Earth. The moon created by Thea's sacrifice serves as our planet's stabilizing influence, moderating Earth's rotational wobble and maintaining relatively stable seasons over geological time. Without this lunar anchor, Earth might have experienced chaotic climate swings that could have prevented the development of complex ecosystems. The collision also fundamentally altered Earth's day length. Before impact, our planet likely rotated much faster, perhaps completing a full day in just 5 hours. The angular momentum added by Thea's collision slowed this rotation to more reasonable intervals, eventually leading to the 24-hour cycle that governs life today. Evidence suggests that Thea itself may have originated much farther from the Sun than previously thought. Recent measurements of oxygen isotopes in deep lunar samples hint that the impactor formed in the outer solar system, possibly carrying with it the water that would later fill Earth's oceans. This makes Thea not just our planet's near destroyer, but potentially the source of the very water that makes life possible. The giant impact hypothesis now represents the scientific consensus for lunar formation, supported by multiple lines of evidence from geochemistry, physics, and computer modeling. Yet many mysteries remain. Scientists continue to refine their understanding of impact dynamics, investigating whether the collision was truly head-on or occurred at an oblique angle. Some researchers propose that multiple smaller impacts may have contributed to the moon's formation, while others explore the possibility that Earth briefly became an exotic object called a synestia, a donut-shaped mass of vaporized rock spinning so rapidly that it defied conventional planetary categories. Future missions may unlock more secrets of this ancient collision. NASA's upcoming Artemis program will return astronauts to the lunar surface, where they plan to collect samples from regions never before explored. These new specimens may contain chemical signatures that reveal additional details about Thea's composition and the precise mechanics of its world-ending encounter with Earth. The story of Thea reminds us that our existence depends upon cosmic violence of unimaginable scale. Without this Mars-sized intruder's catastrophic sacrifice, Earth might have remained a barren, rapidly spinning world without the stabilizing presence of a large moon. The water we drink, the stable seasons we experience, and the very rhythm of our days all trace back to that primordial collision that nearly destroyed our world, but ultimately made it habitable. In the grand cosmic timeline, their impact represents more than destruction. It demonstrates how chaos can become creation, how violence can birth beauty, and how the most devastating events can sometimes plant the seeds for life's greatest triumphs. Every time we gaze up at the moon, we witness the transformed remains of a cosmic collision that shaped our world's destiny 4.5 billion years ago. The debris from that ancient impact continues to influence our planet today. Tidal forces generated by the moon's gravitational pull help drive ocean currents, influence biological rhythms, and even contribute to the gradual slowing of Earth's rotation. What began as cosmic destruction has become an integral part of the delicate planetary machinery that sustains life on our world. This tale of planetary collision and lunar birth illustrates the dynamic, ever-changing nature of our solar system. The calm, orderly arrangement of planets we observe today emerged from billions of years of cosmic chaos, impacts, and gravitational reshuffling. Theia was likely just one of many planetary embryos that roamed the early solar system, most of which were eventually absorbed by the growing terrestrial planets or ejected into interstellar space. As we continue to explore other star systems, astronomers have begun discovering evidence of similar giant impacts around distant suns. Infrared observations reveal warm dust clouds around young stars, possibly the aftermath of recent collisions between forming planets. These observations suggest that the violent process that created our moon may be common throughout the galaxy, with countless worlds experiencing their own versions of the Theia impact. The legacy of our Mars-sized intruder extends beyond Earth and its moon. By adding Theia's mass to our planet, the collision increased Earth's gravitational influence and helped clear our orbital neighborhood of smaller debris. This cosmic housekeeping may have been crucial for establishing the relatively stable conditions that allowed life to evolve without constant bombardment by large impactors. And so the story of Theia becomes the story of ourselves. We are the children of cosmic collision, shaped by forces that dwarf human comprehension. Our bones contain calcium forged in stellar furnaces. Our blood carries iron delivered by ancient impacts. And our very existence depends upon the moon that rose from the ashes of our planet's greatest catastrophe. In this way, the most destructive event in Earth's history became the foundation for everything that followed, a cosmic reminder that sometimes endings are simply beginnings in disguise. What travels through the galaxy without purpose, home, or light? Among the countless stars that populate our Milky Way exists a hidden population far more numerous than planets bound to solar systems. These cosmic orphans drift through interstellar space in eternal darkness, carrying secrets of planetary formation and the potential for both creation and destruction. Astronomers call them rogue planets. These solitary worlds roam the galaxy untethered to any star. Recent discoveries suggest their numbers dwarf even our most ambitious estimates. Studies show that for every 20 free-floating planets wandering the cosmic void, only one remains bound to a stellar parent. The implications stagger the imagination, trillions of worlds drifting alone through the darkness between stars. The story of these planetary nomads begins in the chaotic birth of solar systems. During the first few million years of formation, newly created worlds often engage in gravitational battles for survival. Computer simulations reveal that planetary systems rarely remain stable during their youth. Close encounters between forming planets can send one world spiraling toward its star while ejecting another into the cold depths of space. Some rogue planets escape through encounters with passing stars. When a foreign stellar visitor approaches a young planetary system, its gravitational influence can destabilize orbital patterns that took millions of years to establish. The smaller worlds become casualties of these cosmic interactions, flung outward at velocities exceeding the escape speed of their birth systems. Other planetary exiles result from the natural turbulence of multi planet systems. As young worlds migrate through their natal disks of gas and dust, they occasionally encounter resonance patterns that amplify their orbital eccentricities. These interactions can pump enough energy into a planet's orbit to break the gravitational bonds that hold it to its parent star. Evidence indicates that some rogue planets may never have experienced stellar companionship at all. In the densest regions of stellar nurseries, gravitational collapse can create planet sized objects directly from interstellar gas clouds. These failed attempts at star formation result in brown dwarfs and planetary mass objects that begin their existence as cosmic wanderers. The detection of these invisible giants presents enormous challenges to astronomers. Without starlight to illuminate their surfaces, rogue planets emit virtually no visible radiation. Their discovery requires ingenious indirect methods that exploit subtle effects predicted by Einstein's theory of general relativity. Gravitational microlensing provides the primary tool for finding these hidden worlds. When a rogue planet passes directly between Earth and a distant star, its gravity acts like a cosmic magnifying glass. The planet's mass bends the light from the background star, creating a brief brightening event that can last anywhere from minutes to several months, depending on the planet's mass and distance. This technique has revealed remarkable diversity among free-floating worlds. In 2020, astronomers detected the smallest rogue planet known to date, an Earth mass object designated OGEL 2016 BLG 1928. The microlensing event lasted just 41 minutes, making it the shortest planetary detection ever recorded. This discovery demonstrates that terrestrial mass worlds can survive ejection from their birth systems. At the opposite extreme, observations have identified rogue planets exceeding Jupiter's mass by more than 10 times. These supergiants likely represent the upper boundary of planetary formation, objects too massive to qualify as stars, yet too large to have formed through traditional planet-building processes. Direct imaging techniques have recently begun contributing to rogue planet discoveries. Young worlds retain heat from their formation for millions of years after birth, glowing faintly in infrared wavelengths. Sensitive cameras mounted on the world's largest telescopes can detect this thermal radiation, allowing astronomers to photograph rogue planets directly. The European Southern Observatory's recent survey of the Upper Scorpius region employed this approach to stunning effect. Observations reveal at least 70, and possibly as many as 170, rogue planets in a single patch of sky spanning the constellations Scorpius and Ophius. This represents the largest collection of free-floating worlds ever discovered simultaneously. These findings suggest that rogue planets may be the most common type of planetary object in the galaxy. If similar densities exist throughout the Milky Way, the total population of wandering worlds could reach quadrillions. The galaxy may contain more rogue planets than it has stars by factors of hundreds or thousands. The orbital mechanics of these cosmic wanderers reveal fascinating possibilities for their future evolution. Research indicates that our solar system acts as a gravitational collector capable of capturing passing rogue planets under specific circumstances. The combined gravitational effects of the Sun and the entire Milky Way galaxy create stable capture zones at distances of approximately 4 light years from our star. Rogue planets entering these zones would begin a billion-year journey spiraling slowly inward toward the Sun. The capture process exhibits mathematical properties similar to fractal patterns, with chaotic orbital behaviors reminiscent of the famous Mandelbrot set. These captured worlds would remain gravitationally bound to our solar system indefinitely, never colliding with the Sun but continuously approaching closer orbits. Such scenarios raise intriguing questions about potential consequences for Earth and its neighboring planets. A Jupiter mass rogue planet entering our solar system would fundamentally alter the gravitational architecture that has remained stable for billions of years. The orbital mechanics of all existing worlds would shift dramatically, potentially sending some planets into different orbits or even ejecting them from the system entirely. The effects on Earth could range from subtle changes in seasonal patterns to catastrophic alterations of our planet's orbit around the Sun. The complex interplay between multiple massive objects would make precise predictions nearly impossible, introducing elements of chaos into the previously predictable dance of planetary motion. Paradoxically, some rogue planets may harbor conditions suitable for life, despite their separation from stellar energy sources. Theoretical models suggest that worlds exceeding several Earth masses could retain enough internal heat to maintain liquid water oceans beneath thick ice shells. These subsurface seas would remain isolated from the freezing vacuum of space, potentially providing stable environments for biological processes. The decay of radioactive elements within planetary cores could sustain these hidden biospheres for billions of years. Tidal heating from large moons might provide additional energy sources, particularly if captured satellites maintain eccentric orbits around their rogue planet hosts. Such worlds could serve as arcs carrying life between star systems, seeding new regions of the galaxy with biological complexity. Recent theoretical work has even suggested that some rogue planets might support their own satellite systems. Computer simulations demonstrate that massive worlds can retain moons during their ejection from planetary systems, provided the satellites orbit sufficiently close to their parent planet. These rogue systems could preserve miniature versions of the gravitational relationships that characterize traditional solar systems. The search for rogue planets continues to accelerate with the development of new observational capabilities. The upcoming Nancy Grace Roman Space Telescope will conduct the most comprehensive microlensing survey ever attempted, potentially discovering thousands of additional free-floating worlds. This mission will extend detection sensitivity down to Mars mass objects, revealing the full spectrum of planetary ejection throughout the galaxy. Ground-based surveys are simultaneously expanding their reach through improved camera technologies and automated data processing systems. The Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory, will monitor billions of stars for microlensing events, dramatically increasing the rate of rogue planet discoveries. These observational advances promise to answer fundamental questions about planetary formation and evolution. The relative abundance of different mass rogue planets will provide crucial insights into the mechanisms that govern planetary system architecture. Understanding why some worlds remain bound to their stars while others escape into interstellar space could reshape theories of solar system formation. The study of rogue planets also offers unique opportunities to investigate planetary atmospheres and compositions without interference from stellar radiation. These worlds preserve the chemical signatures of their formation environments, serving as fossil records of conditions in the early galaxy. Spectroscopic analysis of their thermal emission could reveal details about planetary interiors and atmospheric evolution impossible to obtain from star-bound worlds. As detection techniques continue improving, astronomers expect to discover rogue planets throughout the entire mass range, from rocky super-Earths to brown dwarf-like giants. Some predictions suggest that the smallest free-floating objects may be more common than their larger counterparts, implying vast populations of invisible worlds drifting through the spaces between stars. The implications extend beyond simple planetary census taking. Rogue planets represent a significant component of the galaxy's dark matter budget, contributing mass that remains largely unaccounted for in current cosmological models. Their gravitational effects may influence the large-scale structure of stellar formations and the dynamics of galactic evolution. Perhaps most significantly, these wandering worlds challenge our fundamental assumptions about the requirements for planetary habitability. Life may not require the warmth of a nearby star if sufficient energy sources exist within planetary interiors or moon systems. Rogue planets could serve as stepping stones for biological evolution, carrying genetic information across interstellar distances and connecting otherwise isolated stellar environments. The discovery of increasingly numerous rogue planet populations reminds us that the universe contains far more complexity than our Earth-centric perspective might suggest. These invisible giants drift through the darkness in numbers that dwarf conventional solar systems, representing an entirely different class of cosmic environment that may be more common than the planetary arrangements we consider normal. Every few million years, one of these cosmic wanderers passes close enough to our solar system to potentially alter the stable orbital relationships that have persisted throughout Earth's history. Whether such encounters bring destruction or opportunity may depend on factors we cannot yet predict or control. The darkness between stars harbors secrets that continue to surprise and challenge our understanding of planetary science. In contemplating these hidden populations of worlds, we glimpse the dynamic and ever-changing nature of galactic evolution. The planets we observe today represent only a fraction of the worlds that formed during the galaxy's long history. Many more drift silently through the cosmic void, carrying their stories of formation and loss into the infinite darkness that surrounds us all. 445 million years ago, during a period geologists call the Late Ordovician, something catastrophic happened to Earth's protective atmosphere. Marine creatures that had thrived for millions of years suddenly began dying in massive numbers. Coral reefs vanished from the ocean floors. Trilobites, Those ancient arthropods that had dominated the seas disappeared forever from large regions of the planet. Within a few 100,000 years, 85% of all species had vanished. The cause remained a mystery for more than a century after paleontologists first discovered this ancient devastation. No asteroid crater matched the timing. No massive volcanic eruptions left their signature in the rocks. No obvious earthly catastrophe could explain such widespread destruction. The answer may have come from the stars themselves. Recent investigations suggest that supernova explosions within 65 light years of Earth triggered at least two major extinction events in our planet's history. The evidence comes not from the explosions themselves, which leave no permanent traces after a few 100,000 years, but from careful statistical analysis of stellar populations in our cosmic neighborhood. Stars spend most of their lives in peaceful equilibrium. Nuclear fusion in their cores provides the energy to counteract gravitational collapse. Hydrogen atoms fuse into helium, releasing light and heat that can sustain this balance for billions of years. But for stars more massive than 8 times our Sun's mass, this stability cannot last forever. The process begins when these stellar giants exhaust their hydrogen fuel. Unable to maintain the fusion fires that have supported them for millions of years, they begin burning heavier elements in their cores. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each stage proceeds faster than the last, creating a series of nested shells around an increasingly dense core. The final phase happens with stunning swiftness. When the core attempts to fuse silicon into iron, the stellar furnace encounters an insurmountable obstacle. Iron cannot release energy through fusion. Instead of producing the radiation pressure needed to support the star's enormous mass, iron formation actually absorbs energy. The core temperature drops. Gravitational forces suddenly overwhelm all opposition. What follows challenges human comprehension. The core collapses from the size of Earth to roughly 20 kilometers across in less than 1 second. Protons and electrons are crushed together to form neutrons. The implosion rebounds when the core reaches nuclear density, creating a shock wave that propagates outward through the star's outer layers at 30,000 kilometers per second. The explosion that results releases more energy in 10 seconds than our sun will produce during its entire 10 billion year lifetime. Matter accelerated to 30%, the speed of light tears through the star's outer envelope, heating it to temperatures exceeding 100 billion degrees. The dying star becomes briefly brighter than an entire galaxy containing 100 billion normal stars. This cosmic violence creates and disperses the heavy elements essential for life: carbon, oxygen, nitrogen, iron, calcium, all the atoms heavier than hydrogen and helium that compose our bodies and our planet were forged in the nuclear furnaces of massive stars or during their explosive deaths. Supernovae scatter these elements throughout interstellar space, where they become incorporated into new generations of stars and planets. But the same process that enriches the galaxy with life-building materials can also threaten existing life across interstellar distances. The gamma radiation and high-energy particles produced by nearby supernovae can fundamentally alter planetary atmospheres, stripping away protective ozone layers and exposing surface life to lethal doses of ultraviolet radiation. Computer models reveal the devastating sequence of events that would follow a supernova within 65 light years of Earth. High energy photons from the explosion would reach our planet within decades of the initial detonation. These gamma rays would interact with molecules in the upper atmosphere, breaking apart nitrogen and oxygen and converting them into nitrogen oxides. The chemical reactions triggered by this radiation would systematically destroy ozone molecules throughout the stratosphere. Within months, Earth's protective ozone layer could be depleted by 50% or more. The consequences would be immediately visible to any hypothetical observers on the planet's surface, as ultraviolet radiation from the sun increased dramatically. Life forms most vulnerable to ultraviolet damage would suffer first and most severely. Phytoplankton, the microscopic plants that form the foundation of oceanic food webs, would experience widespread die-offs as ultraviolet radiation penetrated deeper into the oceans than ever before. These organisms serve as the primary food source for countless marine species, from tiny zooplankton to massive whales. The collapse of phytoplankton populations would trigger cascading ecological failures throughout the marine biosphere. Small fish dependent on zooplankton would starve. Larger predators would follow as their food sources vanished. Coral reefs, already sensitive to environmental changes, would bleach and die as their symbiotic algae succumb to increased radiation. Terrestrial ecosystems would face similar challenges. Plants unable to tolerate elevated ultraviolet levels would experience reduced photosynthesis, stunted growth, and eventual death. Forests would thin and grasslands would become barren. Animals dependent on these plant communities would lose their food sources and habitat. The atmospheric changes would extend beyond ozone depletion. Nitrogen oxides produced by supernova radiation would react with water vapor to form nitric acid. This would fall as acid rain, further stressing already weakened ecosystems. Ocean chemistry would shift as acidic precipitation altered the pH of surface waters. Recovery would be slow and incomplete. Even after the initial radiation passed, cosmic rays from the supernova remnant would continue affecting Earth's atmosphere for thousands of years. The high energy particles would maintain elevated levels of atmospheric ionization, preventing full ozone recovery and prolonging the period of biological stress. Paleontologists studying the late Ordovician extinction have found patterns consistent with this supernova scenario. The extinction occurred in two distinct pulses, separated by hundreds of thousands of years. The first pulse coincided with global cooling and glaciation, possibly triggered by reduced atmospheric absorption of solar radiation following ozone depletion. The second pulse corresponded with warming and ocean anoxia, suggesting complex climate feedbacks continued long after the initial atmospheric damage. The late Devonian extinction, which occurred 372 million years ago, shows similar characteristics. This event eliminated 70% of all species over a period of several million years. Like the Ordovician event, it involved multiple extinction pulses and appears to have affected marine ecosystems more severely than terrestrial ones. Statistical analysis of supernova rates in our galactic neighborhood supports the possibility that stellar explosions caused both extinctions. Astronomers have cataloged all massive stars within 1,000 light years of Earth, identifying the stellar types most likely to explode as supernovae. They have calculated how frequently these stars would have detonated in the past, accounting for stellar evolution timescales and the changing structure of our galaxy. The results suggest that supernovae capable of causing mass extinctions occur within the critical 65 light-year radius, approximately once every 400 million years. Over the past 500 million years of complex life on Earth, two or three such events would be expected based purely on statistical probability. Current observations identify several nearby supernova candidates that could potentially threaten Earth in the future. Betelgeuse, the red supergiant star forming the shoulder of Orion, lies only 550 light years away and shows signs of approaching the end of its stellar evolution. While too distant to cause a major extinction, a Betelgeuse supernova would be dramatically visible from Earth, appearing as bright as a full moon and remaining visible during daylight for several months. Antares, the red supergiant heart of Scorpius, presents a more concerning scenario. Located approximately 600 light years from Earth, this massive star exceeds our Sun's mass by 12 times and shows the characteristic variability of stars nearing supernova. Though still too far to trigger mass extinction, an Antares explosion would significantly impact Earth's atmosphere and climate. Closer candidates exist, but pose less immediate threat. Ik Pegasi, a white dwarf binary system just 150 light years away, represents the nearest potential supernova to Earth. However, this system would produce a Type Ia explosion, which generates less gamma radiation than the core collapse supernovae of massive stars. The biological effects would be correspondingly reduced. The discovery of iron 60 isotopes in deep sea sediments provides direct evidence that relatively recent supernovae have influenced Earth's environment. This radioactive isotope, produced primarily in stellar explosions, has been detected in ocean floor samples dating to approximately 2 and 8 million years ago. The isotope concentrations suggest that supernovae occurred within 300 light years of Earth during these periods. These relatively recent events may have influenced human evolution in subtle ways. The timing of the more recent supernova coincides with significant climate changes in Africa, including the expansion of grasslands at the expense of forests. Some researchers speculate that increased cosmic radiation from the supernova may have contributed to these environmental shifts, indirectly affecting the evolutionary pressures that shaped early human ancestors. The relationship between supernovas and mass extinctions illustrates the profound interconnectedness of cosmic and biological processes. The same nuclear reactions that create the elements essential for life can, under different circumstances, threaten that life across interstellar distances. The stars that light our galaxy also serve as potential instruments of destruction. This cosmic perspective reveals both the fragility and resilience of life on Earth. Our planet has survived multiple supernova-induced crises over hundreds of millions of years, with life recovering and diversifying after each catastrophic period. The extinctions that eliminated dominant species also created opportunities for new forms of life to emerge and flourish. The fossil record shows that mass extinctions often precede periods of rapid evolutionary innovation. The marine ecosystems that developed after the Ordovician extinction were more diverse and complex than those that preceded it. The late Devonian extinction cleared the way for the expansion of vertebrate life on land. Destruction and creation appear inextricably linked in the cosmic cycle of stellar death and rebirth. Modern civilization faces the same cosmic risks that have threatened life throughout Earth's history. Unlike our evolutionary ancestors, however, We possess the knowledge and technology to predict and potentially mitigate these threats. Advanced telescopes can identify supernova candidates decades or centuries before they explode. Space-based instruments can monitor the health of our planet's ozone layer and atmospheric chemistry. Perhaps most importantly, our understanding of these cosmic threats provides perspective on our place in the universe. We exist within a galaxy where stellar explosions regularly reshape the chemical and physical environment of entire stellar neighborhoods. Our presence on Earth represents not just the product of 4 billion years of biological evolution, but also our planet's remarkable survival through multiple cosmic catastrophes. The heavy atoms in our bodies tell the story of countless stellar deaths that preceded our existence. The iron in our blood, the calcium in our bones, the oxygen we breathe all were forged in stellar furnaces and dispersed by supernova explosions across the galaxy. We are quite literally made of star stuff, the products of cosmic violence transformed into living, thinking beings. In contemplating the role of supernovae in Earth's history, we encounter one of the universe's most profound paradoxes. The stars that threaten life are the same stars that make life possible. Their explosive deaths seed the galaxy with heavy elements, while simultaneously endangering any life that may have evolved on nearby worlds. Creation and destruction dance together in an ancient cosmic ballet that has shaped our galaxy for billions of years. This ongoing stellar cycle continues around us. New stars form from the enriched gas clouds left behind by ancient supernovae. These young stars begin their own journeys toward eventual death and explosion. The process that eliminated the trilobites and devastated 65 million years ago continues to unfold across the outer reaches of our solar system. New worlds, this cosmic traveler measured between 10 and 15 kilometers across, roughly the size of a mountain or small city. It approached our planet at a velocity of 20 kilometers per second, carrying kinetic energy equivalent to 100 million megatons of TNT. When it struck the shallow waters off Mexico's Yucatan Peninsula, it unleashed forces that would reshape life on Earth forever. The asteroid's arrival ended one of the most successful chapters in our planet's biological history. For 165 million years, dinosaurs had dominated terrestrial ecosystems. These remarkable creatures had evolved into forms both massive and delicate, from the enormous sauropods that grazed in prehistoric forests to the swift predators that hunted in ancient grasslands. Their reign seemed secure, their diversity unmatched. Then in a single moment, everything changed. The mechanics of this cosmic catastrophe reveal the incredible power contained within relatively small objects traveling at interplanetary speeds. The Chicxulub impactor, as scientists now call this ancient asteroid, struck Earth at an optimal angle for maximum destruction. Computer simulations show that it hit at approximately 60 degrees above the horizontal, creating conditions that launched the greatest possible amount of vaporized material into the atmosphere. The immediate effects defied comprehension. The impact excavated a crater 150 kilometers across and several kilometers deep. Rock from the Earth's crust was hurled 25 kilometers high, temporarily escaping the atmosphere before falling back as molten droplets across vast regions. The collision formed a rim of mountains taller than the Himalayas around the crater's edge, mountains that have since eroded away but left their geological signature in the underlying rock formations. Within seconds of impact, the asteroid itself had completely vaporized. The enormous kinetic energy of the collision transformed both the impactor and the target rocks into superheated gas and plasma. This transformation released massive quantities of sulfur compounds, carbon dioxide, and water vapor into the atmosphere. The chemistry of the impact site proved particularly unfortunate for life on Earth, as the asteroid struck a region rich in sulfur bearing minerals that amplified the atmospheric effects. The blast generated seismic waves equivalent to a magnitude 11 earthquake, far beyond anything recorded in human history. These shock waves traveled around the planet multiple times, triggering secondary earthquakes and possibly volcanic eruptions thousands of kilometers from the impact site. The Deccan Traps in India, already experiencing volcanic activity, may have intensified their eruptions in response to the seismic energy transmitted through the Earth's interior. Perhaps most devastatingly, the impact launched trillions of tons of fine dust particles into the stratosphere. Recent research has revealed that this dust cloud proved more lethal than previously understood. The particles were so fine that they remained suspended in the atmosphere for up to 20 years, with the most severe effects lasting between 5 and 8 years. During this period, the dust blocked sufficient sunlight to halt photosynthesis across much of the planet's surface. The biological consequences unfolded with merciless efficiency. Plants, unable to capture solar energy, began dying within months of the impact. The collapse of photosynthesis eliminated the foundation of terrestrial food webs. Herbivorous dinosaurs, some weighing dozens of tons, required enormous quantities of plant matter to survive. As vegetation withered and died, these giants faced starvation on a planetary scale. Marine ecosystems suffered equally catastrophic disruption. The impact generated tsunamis that swept across the Atlantic and Pacific Oceans, carrying debris hundreds of kilometers inland. The waves reached heights of more than 300 meters in some coastal regions, completely reshaping shorelines and destroying shallow marine habitats. Microscopic marine organisms, particularly those that built calcium carbonate shells, experienced massive die-offs as ocean chemistry shifted in response to atmospheric changes. The darkness following the impact created what scientists term an impact winter. Surface temperatures dropped by as much as 28 degrees Celsius in some regions, creating conditions similar to a severe ice age. This cooling persisted for several years, long enough to disrupt seasonal patterns and eliminate temperature-sensitive species across multiple continents. Yet, the Chicxulub impact represents only the most recent in a series of cosmic collisions that have shaped Earth's biological history throughout geological time. The geological record reveals at least 60 impacts by objects 5 kilometers or larger during the past 600 million years. Most of these ancient craters have been erased by erosion and plate tectonics, but their signatures remain in the form of shocked minerals and geochemical anomalies preserved in sedimentary rocks. The frequency of these cosmic encounters follows predictable mathematical patterns. Objects approximately 1 kilometer across strike Earth every 500,000 years on average. Impacts by 5-kilometer asteroids occur roughly once every 20 million years. The 10-kilometer objects capable of causing global mass extinctions arrive approximately once every 100 million years, making the Chicxulub event a relatively rare but not unprecedented occurrence. Smaller impacts happen far more frequently and provide opportunities to study asteroid collision mechanics on a more manageable scale. The Chelyabinsk meteorite, which exploded over Russia in 2013, was only 19 meters across, but released energy equivalent to 30 Hiroshima bombs. Objects of this size enter Earth's atmosphere approximately once every 60 to 80 years, usually over unpopulated regions or oceans. The 1908 Tunguska event in Siberia demonstrates the destructive potential of even modest-sized impactors. A 50-meter asteroid exploded in the atmosphere above a remote forest region, flattening trees across more than 2,000 square kilometers. Had this explosion occurred over a populated area, it would have caused casualties comparable to a nuclear weapon. Similar events are expected every 2 to 3 centuries. Modern civilization has developed sophisticated systems to detect and track potential impact threats. NASA's Center for Near-Earth Object Studies monitors more than 28,000 asteroids and comets whose orbits bring them within 50 million kilometers of Earth's path around the Sun. These potentially hazardous objects are cataloged and continuously observed to refine predictions of their future trajectories. The recently completed DART mission demonstrated humanity's first successful attempt to alter an asteroid's orbit through direct impact. The spacecraft struck the small asteroid Dimorphos in September 2022, changing its orbital period by 32 minutes. This achievement proved that kinetic impactors can effectively deflect small asteroids, providing a potential defense mechanism against future threats. Ground-based surveys continue expanding their detection capabilities through automated telescope networks that scan the entire visible sky multiple times each month. The Catalina Sky Survey, Linear, and NEOWISE programs have collectively discovered thousands of near-Earth objects, dramatically improving our understanding of the asteroid population in Earth's cosmic neighborhood. However, detection remains challenging for certain types of impactors. Long-period comets arriving from the outer solar system provide only months or years of advance warning, insufficient time for current deflection technologies. These objects approach from all directions and can achieve velocities exceeding 50 kilometers per second, making them particularly dangerous despite their relative rarity. The role of Jupiter as both protector and threat adds complexity to impact risk assessment. This massive planet's gravitational influence deflects many comets and asteroids away from the inner solar system, reducing the frequency of potential Earth impacts. Jupiter's gravity also captured numerous small bodies over billions of years, gradually clearing the solar system of debris left over from planetary formation. Paradoxically, Jupiter occasionally redirects objects toward Earth rather than away from it. Gravitational interactions with the giant planet can alter asteroid orbits, sometimes sending previously harmless objects on collision courses with terrestrial planets. The same mechanism that protects Earth from most impacts occasionally creates new threats from objects that would otherwise remain safely distant. The asteroid belt between Mars and Jupiter serves as the primary source region for Earth-crossing objects. Gravitational resonances with Jupiter gradually pump up the eccentricities of asteroids in certain orbital zones, eventually ejecting them from the belt. These escaped asteroids enter chaotic trajectories that can bring them close to Earth over timescales of millions of years. Recent discoveries have revealed that asteroid impacts can sometimes benefit life as well as destroy it. The Chicxulub collision, despite its devastating immediate effects, cleared ecological niches that allowed surviving mammalian species to diversify and expand. Without this cosmic intervention, mammals might have remained small, nocturnal creatures living in the shadows of dominant reptilian species. Earlier impacts, during the Archean Eon, when Earth was still in its infancy, may have actually promoted the development of early life. These ancient collisions vaporized portions of the ocean and sterilized surface environments, but they also delivered organic compounds and water from comets and asteroids. The energy from impacts created hydrothermal systems that could have provided suitable environments for the first biological processes. The 3.26 billion year old S2 impact, recently studied through analysis of ancient rock formations in South Africa, demonstrates this dual nature of cosmic collisions. The impactor was 50 to 200 times larger than the Chicxulub asteroid, yet geological evidence suggests that microbial life actually flourished in the aftermath of the impact. The collision generated nutrients and created new ecological opportunities that more than compensated for the initial destruction. These paradoxical effects illustrate the complex relationship between cosmic violence and biological evolution. Mass extinctions eliminate established species, but simultaneously create opportunities for evolutionary innovation. The fossil record shows that major extinction events are often followed by periods of rapid diversification as surviving lineages adapt to fill vacant ecological roles. The search for impact craters continues, revealing new insights into the frequency and effects of cosmic collisions throughout Earth's history. The recently confirmed Hiawatha crater in Greenland, measuring 31 kilometers across, formed 58 million years ago during the Paleocene epoch. This discovery demonstrates that significant impacts occurred even after the Chicxulub event, contributing to ongoing environmental changes during the early Cenozoic era. Advanced dating techniques have revealed that some crater-forming events occurred in clusters, suggesting that Earth occasionally encounters swarms of related objects. The breakup of large comets or asteroids in the outer solar system can create families of smaller fragments that arrive at Earth over periods of thousands or millions of years. These impact storms may have contributed to some of the more complex extinction patterns observed in the geological record. The preservation of impact evidence depends heavily on geological processes that can either protect or destroy crater structures over time. Continental cratons, the ancient stable cores of continents, preserve the oldest impact scars because they experience minimal geological activity. Oceanic crust, constantly recycled through plate tectonics, retains no impact craters older than 200 million years. This preservation bias means that the actual frequency of oceanic impacts remains poorly understood. Since oceans cover more than 70% of Earth's surface, most asteroids and comets likely strike marine environments. These impacts can generate massive tsunamis and alter ocean chemistry without leaving permanent crater structures, making their effects difficult to study through conventional geological methods. The discovery of impact spherules in deep sea sediments provides an alternative approach to studying ancient oceanic collisions. These tiny glass beads form when impact-generated molten droplets cool rapidly during their ballistic flight through the atmosphere. Layers of spherules in ocean floor sediments record impact events that left no other geological traces, revealing a more complete picture of Earth's bombardment history. Future space missions will enhance our understanding of impact processes through direct sampling of asteroids and comets. The recently completed OSIRIS-REx mission returned samples from the asteroid Bennu, providing unprecedented insights into the composition and structure of potentially hazardous objects. Analysis of these samples will inform models of impact effects and guide development of deflection technologies. The proposed NEO Surveyor mission will conduct comprehensive infrared observations of near Earth objects, detecting asteroids that are difficult to observe with ground based telescopes. This space based survey will particularly enhance detection of objects approaching from the direction of the Sun, a blind spot for ground based systems that has historically limited our ability to catalog the complete population of potentially hazardous asteroids. International cooperation in planetary defense continues expanding through initiatives like the International Asteroid Warning Network and the Space Mission Planning Advisory Group. These organizations coordinate global efforts to detect, track, and if necessary, deflect threatening objects. The success of the DART mission has demonstrated that deflection technologies can work in practice, providing confidence that humanity possesses at least rudimentary capabilities to defend against cosmic impacts. The story of stones from the void ultimately reveals both the vulnerability and resilience of life on Earth. Our planet exists within a cosmic shooting gallery where collisions are inevitable over geological timescales. Yet life has not merely survived these encounters acantas, with Zeus and Nevites shaped, challenged, and ultimately strengthened by them. The mammals that inherited the Earth after the dinosaurs' extinction represent just the latest chapter in a 4 billion year story of destruction, survival, and renewal. Each impact crater on Earth tells a story of cosmic violence that temporarily disrupted the planet's biosphere. Yet the persistence of life through multiple impact events demonstrates the remarkable adaptability of biological systems. The same processes that eliminated countless species have also driven evolutionary innovation, creating opportunities for new forms of life to emerge and flourish. In contemplating these cosmic encounters, we gain perspective on both the fragility of individual species and the resilience of life itself. The dinosaurs ruled Earth for more than 160 million years before their cosmic appointment with extinction. Their demise cleared the way for our own evolutionary lineage to develop and eventually achieve the ability to detect and potentially deflect the cosmic threats that continue approaching from the darkness of space. The ongoing dance between Earth and its cosmic visitors continues today. Somewhere in the asteroid belt or the outer solar system, future impactors follow their ancient orbits, unaware that they carry the potential to reshape life on a distant blue world. Our growing ability to detect and track these objects represents humanity's first tentative steps toward controlling our cosmic destiny, transforming us from passive victims of celestial mechanics into active participants in the cosmic drama that has shaped our planet for billions of years. Imagine a frozen metropolis drifting through space, 30 kilometers across and darker than charcoal. Compare this to a typical asteroid of similar size, composed primarily of rock and metal, and you encounter one of the solar system's most intriguing paradoxes. Both objects can threaten Earth with equal ferocity, yet comets possess something asteroids lack: the chemical ingredients for life itself, frozen within their ancient cores. These wandering ice balls represent time capsules from the solar system's infancy, preserving organic molecules and water from the primordial disk that gave birth to the planets. Yet the same celestial objects that may have delivered the building blocks of life to early Earth also possess the potential to extinguish that life through catastrophic impacts far more devastating than their rocky counterparts. The distinction between comets and asteroids extends far beyond their composition. When a comet approaches the inner solar system, solar radiation transforms it into one of nature's most spectacular displays. The sun's heat sublimes the frozen gases, creating a glowing coma that can expand to millions of kilometers across. Dust and gas stream away from the nucleus, forming magnificent tails that can stretch farther than the distance from Earth to the Sun. This dramatic transformation reveals why comets pose unique threats to our planet. As these dirty snowballs heat up, they shed enormous quantities of material, creating debris streams that persist in their orbital paths for thousands of years. When Earth crosses these ancient trails, we witness meteor showers as countless tiny particles burn up in our atmosphere. Occasionally, larger fragments survive the journey to become meteorites, carrying pristine samples of the early solar system. The most famous of these cosmic wanderers follows a predictable schedule that has fascinated humanity for millennia. Halley's Comet returns every 76 years, its elliptical path carrying it from beyond Neptune's orbit to within Venus's distance from the Sun. Historical records document its appearances for more than 2,000 years, with ancient Chinese astronomers noting its passages as early as 240 BCE. But Halley represents just one member of a vast population of comets following much longer cycles. The spectacular comet Hale-Bopp, which graced our skies in 1997, follows an orbit that takes roughly 2,400 years to complete. Its previous visit occurred around 2215 BCE, possibly witnessed by ancient Egyptian astronomers during the reign of Pharaoh Pepi II. Its next return will not occur until approximately 4385 CE. Even more extreme examples exist among the long-period comets that originate from the distant Oort cloud. Comet Neowise, the brightest comet visible to Northern Hemisphere observers since Hale-Bopp, follows a nearly 7,000-year orbit. The last generation to witness this celestial visitor lived during the 5th millennium BCE, when global human populations numbered only 40 million and agriculture was just beginning to develop. The Oort cloud itself remains one of the solar system's most mysterious regions. The spherical shell of icy objects extends from roughly 2,000 times Earth's distance from the Sun to nearly halfway to the nearest star. Astronomers estimate it contains trillions of comet nuclei, representing a mass perhaps 100 times that of Earth. These frozen remnants occupy a realm where the Sun appears as little more than a bright star, and temperatures hover just a few degrees above absolute zero. Occasionally, gravitational perturbations nudge Oort cloud objects toward the inner solar system. The causes of these perturbations range from galactic tides to the gravitational influence of passing stars. When a comet begins its journey from this distant reservoir, it may take millions of years to reach the vicinity of the Sun, accelerating as it approaches and developing the characteristic features that make comets so distinctive. The detection of long-period comets presents extraordinary challenges for modern astronomy. Unlike asteroids that remain visible for years as they follow predictable orbits through the inner solar system. Long-period comets may provide warning times measured in months rather than decades. Their highly elliptical paths make trajectory calculations difficult until multiple observations allow accurate orbital determinations. Comet Swift-Tuttle exemplifies these detection challenges. This 40-kilometer wide object follows a 133-year orbit that brings it relatively close to Earth's orbital path. During the 1990s, preliminary calculations suggested it might collide with our planet during its 2126 return. Subsequent observations refined its orbit and eliminated the immediate threat, but the incident highlighted how difficult it can be to predict the behavior of these cosmic visitors accurately. The threat posed by long-period comets extends beyond individual objects to include the possibility of comet showers triggered by stellar encounters. As our solar system moves through the galaxy, it occasionally experiences close approaches by other stars. These stellar flybys can gravitationally disturb the Oort cloud, sending multiple comets toward the inner solar system simultaneously. The European Space Agency's Gaia satellite has revolutionized our understanding of stellar motions, revealing that approximately 550 stars pass within 150 trillion kilometers of the Sun every million years. About 20 of these encounters occur within 30 trillion kilometers, close enough to significantly perturb objects in the outer Oort cloud. Such close approaches happen roughly once every 50,000 years. The most dramatic example of an approaching stellar encounter involves Gliese 710, a red dwarf star currently located about 63 light-years from Earth. In approximately 1.4 million years, this star will approach within about 16,000 times Earth's distance from the Sun, passing through the outer regions of the Oort cloud itself. Astronomers describe this as potentially the strongest disrupting encounter in our solar system's history. Unlike most stellar flybys, Gliese 710 travels relatively slowly, giving it ample time to exert gravitational influence on Oort cloud objects. Computer models predict that this encounter could send thousands of comets spiraling toward the inner solar system over a period of several million years. Some of these comets would inevitably cross Earth's orbit, potentially triggering impact events during humanity's distant future. Evidence suggests that similar stellar encounters have influenced Earth's history in the past. Geological evidence points to a dramatic increase in comet and asteroid impacts approximately 35 million years ago during the late Eocene epoch. Two major craters, the Popigai crater in Siberia and the Chesapeake Bay crater in Virginia, formed almost simultaneously during this period. Analysis of deep-sea sediments reveals elevated concentrations of helium-3, an isotope common in interplanetary dust, but rare on Earth, supporting the idea of a comet shower during this time frame. The composition of comets adds another dimension to their potential threat. These objects contain not only water ice, but also frozen carbon dioxide, methane, ammonia, and complex organic molecules. When a large comet impacts Earth, it delivers these materials along with enormous quantities of energy. The combination can dramatically alter atmospheric chemistry and climate in ways that rocky asteroid impacts cannot match. The famous Tunguska event of 1908, while likely caused by a small asteroidal object, demonstrates how atmospheric explosions can devastate large areas without leaving permanent craters. A comet of similar size might produce even more dramatic effects due to its lower density and higher volatile content. The object would likely fragment and explode at higher altitudes, spreading its effects across wider areas. Larger comets pose correspondingly greater risks. A 30-kilometer comet impacting Earth would deliver roughly the same kinetic energy as the Chicxulub asteroid that ended the dinosaur era, but with additional effects from its chemical composition. The water vapor and other gases released during impact could persist in the atmosphere for years, potentially causing both greenhouse warming and acid rain, depending on the specific chemistry involved. The irregular shapes and low densities of comet nuclei create additional complications for any potential deflection efforts. Unlike solid asteroidal objects that respond predictably to impact or explosive forces, comets may fragment unpredictably when disturbed. The recent DART mission successfully altered an asteroid's orbit through kinetic impact, but similar techniques applied to comets might simply create multiple threatening fragments rather than harmlessly deflecting a single object. Modern space agencies are developing specialized strategies for comet threat mitigation. These approaches often involve deflection rather than destruction, using gentle continuous forces applied over long periods to gradually alter orbital trajectories. Solar sails, ion drives, and gravity tractors represent potential technologies for slowly nudging threatening comets away from collision courses with Earth. The Deep Impact mission of 2005 provided valuable insights into comet structure and behavior by deliberately colliding with Comet Tempel 1. The impact excavated approximately 25 million kilograms of material, revealing a surface composition much richer in dust than previously expected. These observations suggest that comets may be more fragile than originally thought, with important implications for both natural collision effects and potential deflection strategies. Recent observations have also revealed unexpected diversity among comet populations. Some objects appear to be dormant comets that no longer exhibit active gas and dust production, despite containing substantial quantities of volatile materials. These dark objects become virtually invisible except when they approach close to the Sun, making them particularly difficult to detect and catalog. The study of comets continues, revealing new surprises about these ancient objects. The Rosetta mission's detailed examination of comet 67P/Churyumov-Gerasimenko showed that cometary water has a different isotopic composition than Earth's oceans, challenging theories about comets as the primary source of terrestrial water. However, the mission also confirmed that comets contain complex organic molecules, including some that serve as precursors to amino acids essential for life. These discoveries reinforce the paradoxical nature of comets as both cosmic threats and potential sources of life's ingredients. The same objects that might have delivered organic compounds to early Earth continue to pose long-term risks to established ecosystems. Their dual role as creators and destroyers reflects the complex interplay between cosmic forces and biological evolution throughout our planet's history. The timescales involved in comet threats challenge human planning capabilities. While asteroid surveys can identify potentially dangerous objects decades or centuries before potential impacts, long-period comets may provide warning times insufficient for current deflection technologies. This temporal mismatch between detection and mitigation represents one of the most significant challenges in planetary defense. Future space-based detection systems may extend warning times by identifying incoming long-period comets at greater distances from the Sun. Infrared telescopes positioned at gravitationally stable points in the outer solar system could potentially spot approaching objects years before they become visible to ground-based observatories. Such early warning networks would provide additional time for defensive measures while also advancing our scientific understanding of the Oort cloud and its inhabitants. The philosophical implications of comet research extend beyond immediate practical concerns about planetary defense. These objects represent some of the most pristine materials remaining from the solar system's formation, carrying chemical information about conditions in the primordial solar nebula. Each comet that approaches the Sun offers a unique opportunity to study the processes that shaped our cosmic neighborhood billions of years ago. In contemplating the dual nature of comets, we encounter one of astronomy's most profound ironies. The very objects that may have made life possible on Earth by delivering water and organic compounds also represent ongoing threats to that life's continued existence. Their ancient orbits carry them between the frozen depths of interstellar space and the warm inner regions where planets orbit, bridging the vast scales that separate creation from destruction in our cosmic environment. The story of dirty snowballs continues unfolding as new discoveries reveal additional complexity in these apparently simple objects. Some comets appear to be contact binaries, formed when two separate nuclei gently collided and stuck together. Others exhibit unexpected surface features, including cliffs, boulders, and what appear to be impact craters from collisions with smaller objects during their long journeys through space. As we develop increasingly sophisticated methods for detecting and studying these cosmic visitors, we gain deeper appreciation for their role in shaping the solar system we inhabit today. Every comet that graces our skies carries within its frozen nucleus a message from the distant past, written in the language of ice and dust and organic molecules that remember the conditions present at our solar system's birth. The dance between comets and Earth continues today as it has for billions of years, sometimes bringing destruction, sometimes bringing the materials necessary for life itself. Our growing understanding of these relationships allows us to appreciate both the beauty and the peril inherent in sharing a solar system with these ancient wanderers from the cosmic deep. Across the observable universe, certain stellar deaths unleash energies so vast they can be detected from billions of light years away. These focused beams of gamma radiation represent the most powerful electromagnetic events known to physics, capable of outshining entire galaxies for brief moments. When one of these cosmic searchlights sweeps across Earth, it carries enough energy to fundamentally alter our planet's atmospheric chemistry within seconds. On October 9th, 2022, at precisely 1521 Central European Time, satellites orbiting Earth detected the arrival of such a beam. The European Space Agency's Eye-Integral Telescope registered gamma-ray intensities unlike anything previously recorded. The burst designation GRB 221009 A would soon become famous among astronomers, not merely for its unprecedented brightness, but for its measurable effects on our planet's protective atmospheric layers. This particular gamma ray burst originated from a stellar explosion approximately 1.9 billion light years distant. The light that reached Earth that autumn afternoon had been traveling through space since before our solar system formed. Yet, despite the immense distance involved, the concentrated energy carried by these gamma rays proved sufficient to ionize particles in Earth's upper atmosphere, creating electrical disturbances detectable by sensitive instruments. The China Seismo-Electromagnetic Satellite happened to be positioned perfectly to witness these atmospheric changes. As it orbited 507 kilometers above Earth's surface, the spacecraft recorded dramatic spikes in the electrical field surrounding our planet. These measurements provided the first direct evidence that gamma ray bursts from distant galaxies could significantly influence the upper regions of Earth's ionosphere. Gamma ray bursts emerge from two primary cosmic scenarios, each involving the formation of black holes under extreme conditions. Long-duration bursts, lasting more than 2 seconds, typically result from the core collapse of massive stars at least 8 times more massive than our Sun. These stellar giants exhaust their nuclear fuel and can no longer support their enormous mass against gravitational collapse. The collapse process unfolds with breathtaking speed. Within less than 1 second, the star's core implodes from Earth-sized dimensions to a sphere roughly 20 kilometers across. This compression creates a black hole while simultaneously launching twin jets of material outward at nearly the speed of light. When these jets punch through the star's outer layers, they create the focused beams of gamma radiation that characterize these cosmic explosions. Short-duration gamma-ray bursts follow different pathways to similar endpoints. These briefer flashes, lasting less than 2 seconds, typically occur when two neutron stars spiral into each other after billions of years of orbital decay. The collision destroys both stars while creating a new black hole, accompanied by gravitational waves and intense bursts of electromagnetic radiation across all wavelengths. The rarity of these events contributes to their scientific significance. Statistical analysis suggests that gamma ray bursts capable of seriously affecting Earth's biosphere occur within 10,000 light years of our planet, only once every 10,000 years on average. The October 2022 event represented exactly this type of rare occurrence, providing researchers with an unprecedented opportunity to study the terrestrial effects of distant cosmic violence. The mechanisms by which gamma ray bursts influence planetary atmospheres involve complex chains of chemical reactions triggered by high-energy radiation. When gamma rays penetrate Earth's stratosphere, they break apart nitrogen and oxygen molecules, creating highly reactive chemical species. These fragments recombine to form nitrogen oxides, which systematically destroy ozone molecules throughout the protective layer that shields life from solar ultraviolet radiation. Atmospheric modeling predicts that a nearby gamma ray burst could deplete Earth's ozone layer by 50% or more within months of the initial radiation pulse. The resulting increase in surface ultraviolet exposure would prove lethal to many forms of life, particularly those organisms most sensitive to DNA damage from high-energy photons. Phytoplankton, the microscopic marine plants that form the foundation of oceanic food webs, would experience widespread population crashes. The nitrogen oxides created by gamma-ray radiation would eventually fall back to Earth's surface as nitric acid, creating acid rain across global scales. This chemical precipitation would acidify soils and surface waters while delivering large quantities of nitrogen compounds to terrestrial and aquatic ecosystems. The combined effects of increased ultraviolet radiation and acid precipitation could trigger ecological collapses similar to those observed during major mass extinction events. Some researchers have proposed that gamma ray bursts may have contributed to past extinction crises recorded in Earth's fossil record. The late Ordovician mass extinction, which occurred 445 million years ago, eliminated approximately 85% of all marine species within a relatively brief geological time frame. The extinction patterns observed in ancient rocks show characteristics consistent with the effects predicted for gamma ray burst scenarios. Marine organisms living in shallow water environments suffered disproportionately during the Ordovician extinction, while deep water species showed higher survival rates. This pattern matches the expected effects of increased ultraviolet radiation, which would penetrate deeper into clear ocean waters than into murky coastal environments. Planktonic organisms floating near the surface, where ultraviolet exposure would be most intense, experienced severe population declines. The Ordovician extinction also coincided with rapid climate cooling and the expansion of continental ice sheets. Gamma ray burst hypothesis proponents suggest that the same nitrogen oxides responsible for ozone destruction could have triggered global cooling by creating light-absorbing aerosols in the upper atmosphere. These particles would have reduced the amount of solar energy reaching Earth's surface, potentially initiating the glaciation observed in geological records. Current surveys of nearby stellar populations identify several candidates for future gamma ray burst events within our cosmic neighborhood. Wolf-Rayet stars, which have shed most of their hydrogen envelopes and burn helium at extremely high temperatures, represent the most likely progenitors for long-duration gamma-ray bursts. These massive stars exist in sufficient numbers within several thousand light-years of Earth to create statistical concern about future threats. Eta Carinae, located approximately 7,500 light-years away in the southern constellation Carina, represents perhaps the most famous gamma-ray burst candidate. This hypergiant star exhibits the rapid rotation and low metallicity characteristics associated with collapsar models of gamma-ray burst formation. While still too distant to cause major extinction events, an Eta Carinae gamma-ray burst would create spectacular atmospheric displays visible during daylight hours. Bettinger 104, situated roughly 2,600 light-years from Earth in the constellation Sagittarius, presents a more concerning scenario. This Wolf-Rayet star appears to be oriented so that its rotational axis points roughly toward our solar system. If WR 104 eventually produces a gamma-ray burst, Earth would lie within the narrow cone of concentrated gamma radiation, maximizing the potential atmospheric effects. The October 2022 gamma-ray burst provided valuable insights into the detection and measurement of these cosmic events. Very low-frequency radio waves, used for long-distance communication, showed characteristic disturbances as they bounced between Earth's surface and the ionosphere. These radio signatures offered a new method for identifying gamma-ray burst effects that complement traditional satellite-based gamma-ray detection systems. Lightning detection networks across Europe registered unusual activity during the gamma-ray burst, as the high-energy radiation created electrical disturbances in the atmosphere. These ground-based measurements demonstrated that even distant gamma-ray bursts could produce effects detectable by existing terrestrial monitoring systems, potentially providing early warning capabilities for future events. The duration of atmospheric effects from the 2022 event extended far beyond the initial 7-minute gamma ray pulse. Ionospheric disturbances persisted for several hours after the burst ended, illustrating the complex cascade of chemical reactions triggered by the high energy radiation. These prolonged effects offer insights into how more intense or nearby gamma ray bursts might create lasting atmospheric changes. Research into gamma ray burst effects has revealed the interconnected nature of Earth's atmospheric chemistry. The same ozone layer that protects life from solar ultraviolet radiation also plays crucial roles in atmospheric heating and circulation patterns. Severe ozone depletion could therefore trigger climate changes extending far beyond simple increases in surface radiation levels. The study of gamma ray bursts also provides unique windows into the formation of black holes and the physics of matter under extreme conditions. The jets responsible for gamma radiation achieve velocities exceeding 99% of light speed, creating relativistic effects that compress time and space around the escaping material. These phenomena represent some of the most extreme physical processes occurring in the modern universe. Laboratory experiments using high-power lasers now attempt to recreate the electron-positron pair production that occurs within gamma-ray burst jets. These studies help scientists understand how electromagnetic energy converts to matter under conditions impossible to achieve through any other means. The insights gained contribute to both astrophysical theories and fundamental physics research. Future space missions will enhance our ability to detect and study gamma-ray bursts through improved instrumentation and expanded monitoring coverage. The upcoming European Space Agency's Athena X-ray Observatory will provide unprecedented sensitivity for detecting the X-ray afterglows that follow gamma-ray burst events. These observations will help astronomers trace the expansion and cooling of burst remnants over months and years following the initial explosions. Ground-based gravitational wave detectors have begun coordinating their observations with gamma-ray burst detection networks. Short-duration gamma-ray bursts produced by neutron star mergers should generate both gravitational waves and electromagnetic radiation simultaneously. These multi-messenger observations offer new insights into the fundamental physics of space-time and matter under extreme gravitational fields. The philosophical implications of gamma-ray burst research extend beyond immediate concerns about planetary protection. These events demonstrate that Earth exists within a universe where distant stellar processes can directly influence biological evolution across galactic distances. The elements essential for life were forged in stellar cores and distributed by explosive stellar deaths, creating a cosmic connection between star formation and biological complexity. Each gamma-ray burst that sweeps across Earth carries information about stellar evolution, black hole formation, and the chemical enrichment of galaxies throughout cosmic history. The same processes that occasionally threaten life also created the heavy elements necessary for planet formation and biological chemistry. This duality reflects the complex relationship between destruction and creation that characterizes cosmic evolution on all scales. The detection capabilities developed for gamma-ray burst research also serve broader astronomical purposes. The satellites and instruments designed to monitor these events contribute to our understanding of solar flares, magnetospheric dynamics, and atmospheric chemistry. These interdisciplinary applications demonstrate how research into cosmic threats often produces benefits extending far beyond planetary defense considerations. The 2022 gamma ray burst will likely remain the brightest ever recorded for decades or centuries to come. Statistical models predict that events of similar intensity reach Earth approximately once every 10,000 years, making GRB 221009 a once in a lifetime scientific opportunity. The data collected during this event will inform atmospheric models and extinction theories for generations of researchers. As our detection networks become more sophisticated and our understanding of gamma ray burst physics improves, we gain deeper appreciation for the delicate balance that maintains Earth's habitability. The same atmospheric chemistry that makes our planet suitable for complex life also makes it vulnerable to disruption by cosmic events occurring billions of light years away. The story of gamma ray bursts ultimately illustrates the vast scales of energy and distance that characterize our universe. A star that died before our solar system formed could, under the right circumstances, fundamentally alter the chemistry of Earth's atmosphere within seconds. These beams of annihilation remind us that our planetary home exists within a dynamic cosmos where the most distant events can reach across space and time to touch our world. The ongoing research into these cosmic phenomena continues revealing new connections between stellar evolution, atmospheric chemistry, and the history of life on Earth. Each gamma ray burst detected adds another piece to the puzzle of how cosmic violence and biological evolution have interacted throughout our planet's long history, shaping the world we inhabit today. How curious it seems that the very star, which enables all life on Earth, should also possess the power to disrupt the technological civilization that star has made possible. Our sun, that steady beacon of warmth and light, occasionally experiences fits of activity so intense they can reach across 93 million miles of space to interfere with the delicate electronic systems upon which modern society depends. Throughout most of human history, these solar outbursts passed unnoticed, save for their most spectacular manifestation, the northern and southern lights dancing across polar skies in brilliant displays of green, red, and purple. Indigenous peoples created legends to explain these ethereal curtains of light, while ancient Chinese astronomers recorded their observations in imperial chronicles. None suspected that these beautiful phenomena were merely the visible symptoms of powerful electromagnetic storms originating from the sun's turbulent atmosphere. The first hint of the sun's capacity for technological disruption came during the mid-19th century, when humanity had just begun harnessing electricity for long-distance communication. The newly installed telegraph networks, spanning continents, represented the pinnacle of Victorian engineering achievement, carrying news and commercial information across vast distances in mere minutes rather than weeks. On September 1st, 1859, British astronomer Richard Carrington was conducting his routine solar observations from his private observatory in Surrey. Through his telescope, he witnessed something unprecedented. Two intensely bright patches suddenly appeared on the sun's surface, blazing with such brilliance that they were visible against the solar disk itself. Carrington had become the first human to directly observe a solar flare. 17 hours later, Earth experienced the consequences of that solar eruption. The most intense geomagnetic storm in recorded history began unfolding as billions of tons of electrified solar material, hurled into space by the flare, collided with our planet's magnetic field. The resulting electromagnetic disturbances were so severe that auroras appeared as far south as the Caribbean, Rome, and Hawaii, regions where they had never been seen before. Telegraph systems across North America and Europe began behaving erratically as currents induced by the geomagnetic storm flowed through the copper wires. Many operators received electric shocks from their equipment. Telegraph offices caught fire as the induced currents overwhelmed the primitive electrical systems. Some telegraph lines continued operating even after their power sources were disconnected, drawing energy directly from the geomagnetic disturbances rippling through the atmosphere. The Carrington event, as this incident became known, demonstrated that solar activity could directly affect human technology across global scales. Yet in 1859, the world's electrical infrastructure was limited to a few thousand miles of telegraph cables. The same solar storm occurring today would encounter a planet whose every aspect of daily life depends upon vulnerable electronic systems. Solar flares and coronal mass ejections represent two related but distinct forms of solar violence. Solar flares are intense bursts of electromagnetic radiation released when twisted magnetic field lines in the sun's atmosphere suddenly reconnect and release enormous quantities of stored energy. These flashes of radiation span the entire electromagnetic spectrum, from radio waves to gamma rays, and travel toward Earth at the speed of light. Coronal mass ejections follow different physics and timescales. These events occur when magnetic field restructuring in the solar corona launches billions of tons of superheated plasma into interplanetary space. Unlike the instantaneous radiation of solar flares, coronal mass ejections are massive clouds of electrified gas that lumber through space at speeds typically ranging from 300 to 3,000 kilometers per second. The journey time for coronal mass ejections to reach Earth varies dramatically depending on their initial velocity. The fastest storms can traverse the distance between Sun and Earth in as little as 15 hours, while slower eruptions may take several days to complete their interplanetary voyage. This variable timing creates challenges for space weather forecasters, attempting to predict when geomagnetic storms will begin affecting terrestrial systems. Modern satellites serve as our early warning system for approaching solar storms. Spacecraft positioned between Earth and Sun continuously monitor solar wind conditions, measuring the speed, density, and magnetic orientation of particles streaming from our star. When instruments detect the characteristic signatures of an approaching coronal mass ejection, ground-based systems have hours or sometimes days to prepare for the coming geomagnetic disturbance. The interaction between solar storms and Earth's magnetosphere creates a complex cascade of effects throughout our planet's electromagnetic environment. When a coronal mass ejection strikes the magnetosphere's outer boundary, it compresses the entire magnetic structure surrounding Earth. The normally bow-shaped magnetosphere flattens against the planet's sunlit side while extending its tail-like region far into the night. These magnetospheric distortions generate electrical currents in the upper atmosphere that can induce corresponding currents in conducting materials on Earth's surface. Long-distance power transmission lines are particularly vulnerable to these geomagnetically induced currents, which can overload transformers and cause widespread blackouts. The March 1989 geomagnetic storm demonstrated this vulnerability when it collapsed the Hydro-Quebec power grid, leaving 6 million people in eastern Canada without electricity for 9 hours. High voltage transformers represent critical vulnerabilities in modern power networks. These massive devices, often weighing hundreds of tons, require months or years to manufacture and replace. A severe geomagnetic storm could damage dozens of transformers simultaneously across entire continents, creating prolonged blackouts that would affect everything from water treatment plants to fuel distribution systems. Satellites orbiting Earth face even more direct threats from solar storms. The high energy particles associated with coronal mass ejections can penetrate satellite electronics, causing temporary malfunctions or permanent damage. Solar panels degrade under intense particle bombardment, reducing power generation capabilities. Navigation systems experience errors as the charged particles interfere with signal transmission between satellites and ground receivers. The global positioning system, upon which countless applications now depend, becomes unreliable during severe geomagnetic storms, and geomagnetic systems lose precision navigation capabilities, forcing airports to implement costly delays and alternate landing procedures. Emergency services, shipping companies, and precision agriculture operations all suffer disruptions when GPS signals become corrupted by space weather effects. Radio communications experience degradation across multiple frequency bands during solar storms. High frequency radio signals used for long distance communication by airlines, shipping companies, and emergency services can become completely unusable as the ionosphere becomes highly disturbed. The same ionospheric changes that create beautiful auroras also reflect, absorb, or scatter radio waves in unpredictable ways. Space weather forecasters have developed increasingly sophisticated models to predict the arrival and intensity of solar storms. NOAA's Space Weather Prediction Center operates around the clock, issuing warnings and watches for various types of space weather events. These forecasts help power grid operators adjust their systems to minimize damage. Airline companies reroute flights away from polar regions where radiation exposure is greatest, and satellite operators place their spacecraft in protective modes. The economic implications of severe space weather events have attracted increasing attention from governments and insurance companies. A Congressional Budget Office report estimated that a Carrington level event occurring today could cause economic losses ranging from hundreds of billions to several trillion dollars. The widespread integration of electronic systems into every aspect of modern life has created vulnerabilities that did not exist during previous centuries. Recent solar activity has provided valuable opportunities to study space weather effects on contemporary technology. The May 2024 solar maximum produced numerous strong geomagnetic storms that disrupted GPS signals, interfered with precision agriculture operations, and triggered protective shutdowns at some power facilities. These events, while disruptive, were far less intense than the Carrington event, offering glimpses of what a truly severe solar storm might produce. Solar cycle variations create predictable patterns in space weather activity. The sun's magnetic field reverses every 11 years, with peak activity occurring during solar maximum periods when sunspot numbers reach their highest levels. During these active periods, solar flares and coronal mass ejections occur with increased frequency and intensity, creating elevated risks for technological systems. However, the relationship between solar cycle phase and individual storm intensity remains complex. The Carrington event occurred during a relatively modest solar maximum, with sunspot numbers that have been exceeded in many subsequent cycles. This suggests that the Sun can produce extreme space weather events during almost any phase of its activity cycle, making long term predictions challenging. Climate research has revealed intriguing connections between solar activity and Earth's atmospheric systems. Periods of reduced solar activity, such as the Maunder minimum from 1645 to 1715, correspond with cooler global temperatures and altered weather patterns. While the mechanisms linking solar variability to climate remain subjects of active research, the correlations demonstrate that our star's behavior influences Earth's environment in subtle but measurable ways. The development of space weather research has revealed the Sun's true nature as a dynamic, ever changing star whose activity directly affects conditions throughout the solar system. Rather than the steady, unchanging beacon it appears to be from Earth's surface, the Sun exhibits complex magnetic behaviors that create a constantly varying environment of particles and fields extending far beyond the orbit of Pluto. International cooperation in space weather monitoring continues expanding as more nations develop space based assets vulnerable to solar storms. The European Space Agency, Japan, China, and other space agencies contribute observations and forecasting capabilities to a global network designed to track solar activity and its effects. This collaboration reflects the universal nature of space weather threats, which recognize no political boundaries. Future space missions will enhance our ability to understand and predict solar activity. The upcoming Solar Orbiter mission will provide unprecedented views of the Sun's polar regions, areas that play crucial roles in generating solar storms but remain poorly understood. Ground based solar telescopes are achieving remarkable resolution, allowing astronomers to observe magnetic field changes that precede major eruptions. As human activities expand beyond Earth's protective magnetosphere, space weather becomes an even more pressing concern. Astronauts on deep space missions will face direct exposure to solar particle radiation without the shielding provided by Earth's magnetic field. Future lunar bases and Mars expeditions will require sophisticated warning systems and protective measures to ensure crew safety during solar storms. The study of solar activity has also provided insights into the behavior of other stars throughout the galaxy. Young stars often exhibit far more violent magnetic activity than our middle aged sun, producing superflares thousands of times more powerful than anything our solar system has experienced. These observations suggest that Earth has been fortunate to orbit a relatively well behaved star during the crucial period when complex life was developing. The relationship between solar activity and technological vulnerability illustrates one of modern civilization's most ironic dependencies. The same nuclear fusion processes that make Earth habitable also generate the magnetic disturbances that threaten our electronic infrastructure. As our reliance on technology increases, our vulnerability to solar storms grows correspondingly. The Powdervortingengehen and VOR resilient technologies offers hope for reducing space weather impacts. Power grid operators are installing equipment designed to withstand geomagnetically induced currents. Satellite manufacturers are incorporating better radiation, shielding, and error correction systems. Communication networks are developing backup systems that can maintain service during ionospheric disturbances. Yet the fundamental challenge remains. We have built a technological civilization that depends upon the continued good behavior of a nuclear furnace 93 million miles away. Every 11 years, that furnace reaches peak activity levels that have historically produced events capable of disrupting human activities across entire continents. The next solar maximum approaches, carrying with it the potential for space weather events that could test the resilience of our interconnected world. The story of the sun's violent moods ultimately reflects the delicate balance upon which modern life depends. We have become accustomed to the reliable operation of electronic systems that make possible everything from international commerce to emergency services. Yet these same systems exist within an electromagnetic environment that our star can alter dramatically within hours of a solar eruption. Understanding and preparing for space weather represents one of the unique challenges facing technological civilization. Unlike most natural disasters, which affect limited geographical areas, severe geomagnetic storms can simultaneously disrupt systems across entire hemispheres. The solutions require international cooperation, long term planning, and acceptance that we share our solar system with a star whose behavior we are only beginning to understand. In contemplating our relationship with the sun, we encounter the profound interdependence that characterizes life on Earth. The same stellar processes that warm our planet and drive photosynthesis also create the magnetic disturbances that can disrupt the technological systems we have come to view as reliable and permanent. This cosmic irony serves as a reminder that even our most advanced achievements remain subject to forces originating from the heart of our solar system, where hydrogen atoms fuse into helium in a process that both sustains and occasionally threatens the electronic civilization that has emerged on this small planet orbiting our temperamental star. The universe contains objects whose magnetic fields can rip apart human atoms from distances of nearly 1,000 kilometers. These exotic remnants of stellar death possess magnetism so intense that physics itself begins to behave differently in their vicinity. Known as magnetars, they represent nature's most extreme magnetic experiments, concentrated into spheres barely 20 kilometers across, yet containing more mass than our entire sun. On December 27th, 2004, Earth experienced the consequences of encountering one such monster from across the galaxy. Satellites orbiting our planet suddenly registered the brightest burst of gamma radiation ever recorded from beyond our solar system. The source lay 42,000 light years away in the constellation Sagittarius, yet the intensity of its eruption proved sufficient to compress our magnetosphere and alter the chemistry of the upper atmosphere. The object responsible for this interplanetary assault bears the designation SGR 1806-20, a magnetar whose magnetic field strength defies easy comprehension. Current measurements indicate field intensities exceeding 100 trillion times Earth's magnetic environment. To appreciate this extreme, consider that if SGR 1806-20 were positioned halfway to the moon, its magnetic influence would erase every piece of magnetic data on our planet's surface. The December burst released more energy in 1/10 of a second than our sun will produce over the next 150,000 years. This extraordinary output resulted from what astrophysicists term a starquake, a fracturing of the magnetar's crystalline crust under the immense stress of its own magnetic field. The resulting explosion registered magnitude 32 on theoretical seismic scales, dwarfing any earthquake in terrestrial experience. Magnetaires represent the final stage in the evolution of the most massive stars in our galaxy. When stars exceeding 8 solar masses exhaust their nuclear fuel, gravitational collapse compresses their cores into objects of unimaginable density. A teaspoon of magnetaire material would weigh approximately 6 billion tons on Earth, creating conditions where atomic nuclei are crushed together into seas of pure neutrons. The extreme magnetic fields that define these objects arise through processes that push the boundaries of known physics. Current models suggest that rapid rotation combined with intense heat in newly formed neutron stars can trigger dynamo effects that amplify weak inherited magnetic fields by factors of millions or billions. The Taylor-Sprout dynamo mechanism, proposed by theoretical physicists decades ago, appears capable of generating the observed field strengths through turbulent convection in the protoneutron star's interior. These magnetic titans exist in a state of perpetual instability. The tremendous forces generated by their field lines create constant stress on the neutron star's rigid crust. Occasionally, this stress exceeds the breaking point of matter itself, causing sudden fractures that release stored magnetic energy as intense bursts of gamma radiation. The resulting starquakes can trigger emissions visible from thousands of light years away. The effects of magnetar radiation extend far beyond simple electromagnetic emissions. The intense fields surrounding these objects create regions where matter behaves according to quantum mechanical principles rarely observed in nature. Electron-positron pairs spontaneously appear and annihilate in the vacuum near the magnetar's surface. Atoms cannot maintain their normal structure within several hundred kilometers of the strongest examples. Laboratory experiments demonstrate that magnetic fields approaching magnetar intensities would fundamentally alter chemical bonding between atoms. The orbital shapes of electrons would become so distorted that familiar elements would exhibit completely different properties. Hydrogen atoms would compress into needle-like structures, while more complex elements would cease to exist as stable configurations. The rarity of magnetars adds to their mystique. Astronomical surveys have identified only 30 confirmed examples within our entire galaxy, making them among the most uncommon objects in the known universe. Theoretical calculations indicate that perhaps 1 in 10 core collapse supernovae produces a magnetar rather than a conventional neutron star or pulsar. One particularly enigmatic example has captured scientific attention through its unusual behavior and mysterious origin. SGR 0501 plus 4516, nicknamed the Zombie Star by popular media, races through our galaxy at velocities exceeding 177,000 kilometers per hour. This remarkable speed, combined with trajectory analysis, suggests an origin story that challenges conventional understanding of magnetar formation. Traditional models predict that magnetars should remain near their birthplace supernova remnants for thousands of years after formation. However, detailed observations using the Hubble Space Telescope and ESA's Gaia spacecraft reveal no associated supernova debris anywhere along SGR 0501 plus 4,516's historical path. The magnetar appears to have emerged from empty space, defying explanation through standard stellar evolution theories. Alternative formation scenarios propose that some magnetars might originate through white dwarf collapse rather than massive star explosions. In this unusual pathway, a white dwarf accumulates material from a companion star until it reaches critical mass. Instead of exploding as a type higher supernova, the white dwarf undergoes direct collapse into a neutron star, potentially explaining how magnetars could form without obvious supernova signatures. The implications of this alternative mechanism extend beyond magnetar studies into broader astrophysical mysteries. Fast radio bursts, those enigmatic flashes of radio energy from distant galaxies, often originate from regions too old to host massive star explosions. If magnetars can form through white dwarf collapse, they could persist in ancient galactic populations where conventional neutron star formations ceased billions of years ago. The study of magnetars has revealed fascinating connections between stellar evolution and fundamental physics. These objects serve as natural laboratories where magnetic field strengths exceed anything achievable through terrestrial technology. The exotic states of matter existing near magnetar surfaces provide insights into quantum chromodynamics and the behavior of neutrons under extreme conditions. Recent theoretical work suggests that magnetar magnetic fields undergo complex evolutionary cycles over millions of years. Young magnetars exhibit the strongest fields and most frequent bursting activity. As these objects age, their fields gradually decay through processes not fully understood, eventually transforming them into more conventional neutron stars. This evolution explains why most observed magnetars appear relatively young, despite the billions of years available for their formation. The December 24 burst from SGR 1806 to 20 provided unprecedented data about magnetar physics and their effects on planetary environments. The gamma radiation that reached Earth triggered increased ionization throughout the upper atmosphere, creating temporary radio blackouts and enhanced auroral displays. These effects demonstrate that magnetar outbursts can influence planetary conditions across interstellar distances. Scientists have calculated that a similar burst occurring within 10 light years of Earth would have catastrophic consequences for our biosphere. The intense gamma radiation would strip away significant portions of the ozone layer, exposing surface life to lethal doses of ultraviolet radiation. Such an event could trigger mass extinction comparable to those observed in the geological record. Fortunately, the nearest known magnetar lies approximately 9,000 light-years from Earth in the constellation Carina. This distance places it well beyond the range where normal magnetar activity could seriously threaten our planet. However, the possibility of closer examples remaining undetected continues to motivate surveys for these elusive objects. The search for additional magnetars faces significant observational challenges. These objects spend most of their existence in quiescent states, emitting only faint X-ray radiation detectable by the most sensitive space-based instruments. Only during rare outbursts do magnetars become bright enough for easy identification, creating a selection bias toward the most active examples. Modern X-ray telescopes have revolutionized magnetar research through their ability to monitor large areas of sky continuously. The Swift Gamma Ray Burst Explorer, originally designed to study distant supernovae, has discovered several new magnetars through their characteristic emission patterns. Future missions promise even greater sensitivity for detecting the subtle signatures of dormant magnetars. The extreme conditions surrounding magnetars make them ideal test beds for theories of gravity and spacetime. The intense gravitational fields near neutron star surfaces approach the regime where general relativity predicts significant deviations from Newtonian mechanics. Precision timing observations of magnetar emissions could reveal gravitational wave signatures from crustal fractures or magnetic field reconfigurations. Laboratory astrophysics experiments using high powered lasers attempt to recreate the exotic plasma conditions found in magnetar atmospheres. These investigations probe the interaction between matter and magnetic fields at intensities impossible to achieve through conventional means. The resulting data help constrain theoretical models of magnetar structure and evolution. The study of magnetars also illuminates the broader population of neutron stars throughout the galaxy. These objects represent the most common outcome of massive star evolution, yet their properties remain poorly understood due to observational limitations. Magnetars, despite their rarity, provide detailed insights into neutron star physics that apply to the entire population. As observational techniques continue improving, astronomers expect to discover additional examples of unusual magnetars like SGR 0501 plus 4516. Each new detection adds pieces to the puzzle of how these extreme objects form and evolve. The diversity already observed among the small sample of known magnetars suggests that many surprises await discovery. The philosophical implications of magnetar research extend beyond astrophysics into fundamental questions about the nature of matter and energy. These objects demonstrate that the universe regularly achieves physical conditions far beyond human experience or technological capability. In their brief, violent outbursts, magnetars compress millions of years of stellar energy output into fractions of seconds. The December 24 event serves as a reminder that Earth exists within a galaxy containing forces of almost incomprehensible magnitude. While the vast distances between stars provide protection from most cosmic violence, the reach of magnetar gamma ray bursts demonstrates that no planetary system remains completely isolated from the broader galactic environment. Future research into magnetars will likely focus on understanding their internal structure and magnetic field evolution. Advanced computer simulations attempt to model the complex interactions between matter, magnetism, and gravity in these extreme environments. Such studies may eventually explain how nature generates and maintains magnetic fields trillions of times stronger than anything achieved through human technology. The connection between magnetars and other high-energy astrophysical phenomena continues generating scientific interest. These objects may play roles in cosmic ray acceleration, gravitational wave production, and the chemical evolution of galaxies through their energetic outbursts. Each magnetar burst potentially affects the interstellar medium across hundreds of light years, influencing star formation and planetary system development. The story of magnetic monsters ultimately illustrates the universe's capacity for creating conditions that challenge our understanding of physical laws. In transforming stellar cores into objects barely larger than cities yet more massive than stars, nature demonstrates that the familiar world of everyday experience represents only a tiny fraction of possible physical states. These exotic remnants of stellar death continue their lonely journeys through the galaxy, occasionally announcing their presence through outbursts that briefly outshine entire galaxies. Their existence reminds us that the cosmos contains phenomena so extreme that they border on science fiction, yet operate according to the same physical principles that govern more familiar aspects of our universe. As we continue studying these magnetic titans, we gain deeper appreciation for the dynamic, ever changing nature of stellar evolution and galactic ecology. The magnetars racing through space at tremendous velocities carry within their exotic matter the compressed history of massive stars that lived and died billions of years before our solar system formed. Each gamma ray burst from a distant magnetar brings to Earth a message written in the language of physics, pushed to its absolute limits. These communications from the extreme universe expand our understanding of what is possible when matter, energy, and magnetic fields interact under conditions that transform the very nature of atoms and space itself. Throughout the galaxy, approximately 200 billion stars move through space in complex orbital patterns around the galactic center. Our sun participates in this grand dance, completing one circuit of the Milky Way every 225 million years, while bobbing up and down through the galactic plane like a cosmic carousel horse. Occasionally, this orbital motion brings other stars close enough to our solar system to fundamentally alter the gravitational balance that has persisted for billions of years. 70,000 years ago, when modern humans were beginning their migration out of Africa and Neanderthals still inhabited European caves, our solar system received a brief but significant celestial visitor. A small red dwarf binary system approached closer to the Sun than any star had in millions of years, passing within roughly 52,000 astronomical units of our home. This distance may sound vast by terrestrial standards, yet it placed this intruder well within the boundaries of the Oort cloud, that vast spherical shell of comets surrounding our planetary family. The visiting system carries the designation Schultz's star, named after the German astronomer who discovered it in 2013. The primary component is a red dwarf with only 9% of our sun's mass, accompanied by a brown dwarf companion containing about 6% of solar mass. Together, these objects form a binary pair that currently resides 22 light-years away in the constellation Monoceros, racing through space at velocities exceeding 80 kilometers per second. The discovery of this ancient encounter began with a paradox. Astronomer Eric Mamajek noticed that Schultz's star exhibited almost no sideways motion across the sky, despite being relatively nearby. Most stars show measurable proper motion over time as they pursue their galactic orbits, yet this particular system appeared nearly stationary against the background of more distant stars, suggesting it was moving either directly toward or directly away from our solar system. Doppler shift measurements resolved the mystery. The light from Schultz's star showed a pronounced redshift, indicating rapid recession from Earth. Simple calculations revealed that this high radial velocity, combined with minimal proper motion, could only result from a close passage in the relatively recent past. Within 15 minutes of recognizing this pattern, Mamajek and his colleagues had determined that the star must have approached within a light year of the Sun approximately 70 to 80,000 years ago. Confirmation of this stellar encounter came through detailed computer simulations that traced the star's motion backward through time. Out of 10,000 possible orbital trajectories, 98% pass through the outer regions of the Oort cloud. This statistical consistency provided strong evidence that the flyby had indeed occurred as calculated. The gravitational effects of this close passage left lasting signatures throughout the outer solar system. Researchers analyzing the orbital characteristics of 339 objects following hyperbolic trajectories found statistically significant patterns in their apparent origins. Instead of being randomly distributed across the sky, these objects showed a pronounced concentration in the constellation Gemini, precisely matching the predicted trajectory of Scholz's star during its ancient passage. Computer models suggest that the star's gravity perturbed numerous Oort cloud objects during its flyby, sending some on trajectories that eventually brought them into the inner solar system. The statistical clustering of hyperbolic object origins provides observational evidence that stellar encounters can indeed reshape the architecture of distant comet populations over timescales of tens of thousands of years. While the Scholz's star encounter provides fascinating insights into past stellar interactions, an even more dramatic event awaits in our solar system's future. Gliese 710, an orange dwarf star currently located 62 light-years away in the constellation Serpens, approaches our neighborhood on a trajectory that will bring it far closer than any known stellar encounter in the past or projected future. Unlike Scholz's star, which skirted the outer edges of the Oort cloud, Gliese 710 will plow directly through the inner regions of this comet reservoir. Current predictions based on precise measurements from the European Space Agency's Gaia satellite indicate the star will pass within approximately 10,500 astronomical units of the Sun in about 1,280,000 years. The approaching star possesses roughly 60% of our Sun's mass and 58% of its radius. Despite being smaller and cooler than our star, with a surface temperature of only 3,870 degrees Celsius compared to the Sun's 5,500 degrees, Gliese 710 will appear dramatically bright during its closest approach. Calculations indicate it will reach an apparent magnitude of negative 2.7, making it brighter than all planets except Venus and comparable to the brightest stars in our current night sky. The gravitational influence of this approaching star will extend far beyond its brief moment of maximum brightness. As Gliese 710 passes through the Oort cloud at 14.5 kilometers per second, its gravity will disturb countless comet nuclei, sending showers of these ancient ice balls toward the inner solar system over periods spanning several million years. Computer simulations predict that the encounter will increase the semi-major axis of Oort cloud objects by approximately 1.7%, while causing population losses ranging from 0.019 to 0.117%. While these percentages may appear small, they translate to billions of individual comets experiencing orbital modifications sufficient to send them on long journeys toward the Sun and planets. The consequences of this comet bombardment remain difficult to predict precisely. Some of these redirected objects will undoubtedly cross Earth's orbit, potentially increasing the probability of major impact events. However, the timescales involved span millions of years, making it impossible to determine whether any specific impacts will threaten our planet or its potential future inhabitants. The discovery and analysis of stellar encounters like these have been revolutionized by the Gaia space mission. This European Space Agency observatory has measured the positions, distances, and motions of more than 1 billion stars with unprecedented precision. The resulting database allows astronomers to calculate stellar trajectories both backward and forward in time, revealing the dynamic nature of our galactic neighborhood. Gaia's extraordinary capabilities have already identified several other notable stellar encounters. The mission has mapped the approach of binary systems that influenced planetary formation in young stellar systems, demonstrating how gravitational interactions between stars can reshape entire families of worlds during their formation processes. One particularly intriguing example involves the HD 106906 system, where a planet orbiting a young binary star appears to have been kicked into an extremely distant orbit by the combined gravitational effects of the central binary and a passing stellar system. Analysis of Gaia data revealed that another binary pair approached this system between 2 and 3 million years ago, providing the additional gravitational nudge needed to stabilize the planet's otherwise unstable trajectory. These discoveries illustrate the complex interplay of gravitational forces that shape planetary system architecture over millions of years. Close encounters between stars can eject planets entirely, alter their orbital characteristics, or in some cases, capture objects from other systems. The solar system's current configuration represents the end result of billions of years of such interactions, with each encounter leaving subtle imprints on the arrangement of planets, asteroids, and comets. The study of stellar flybys has revealed that our perception of a stable, unchanging solar system reflects only the limited timescales of human observation. On cosmic timescales, gravitational encounters with passing stars represent regular events that continually modify the outer architecture of planetary systems. Every few million years, another star approaches close enough to influence the orbits of distant objects, ensuring that the solar system's structure evolves continuously over geological time. Statistical analysis of stellar motions indicates that approximately 550 stars pass within 150 trillion kilometers of the Sun every million years. About 20 of these approaches occur within 30 trillion kilometers, close enough to significantly influence Oort cloud dynamics. Such close encounters happen roughly once every 50,000 years, making them rare from human perspectives, but routine features of galactic evolution. Future missions will enhance our ability to predict and study these stellar encounters. Advanced space telescopes will extend Gaia's capabilities by measuring stellar positions and motions with even greater precision over longer baselines. These improvements will allow astronomers to detect approaching stars decades or centuries before their closest approach, providing ample time to study their potential effects on solar system dynamics. The identification of approaching stellar visitors also offers opportunities for detailed scientific observation. As stars like Gliese 710 draw closer over the coming millennia, they will become increasingly accessible to study with advanced telescopes and space probes. Future generations of astronomers may be able to examine these stellar systems in unprecedented detail, potentially discovering planets, brown dwarfs, or other objects accompanying the primary stars. The possibility of planetary systems accompanying approaching stars raises intriguing questions about the potential for gravitational capture. In principle, objects orbiting visiting stars could become gravitationally bound to our solar system under specific circumstances. Conversely, some of our own outer system objects might be captured by passing stellar systems, beginning new journeys through the galaxy as part of different planetary families. Research into stellar encounters has also revealed connections between these events and the broader chemical evolution of the galaxy. When stars approach closely enough to perturb Oort cloud objects, they may trigger comet showers that deliver primitive materials from the outer solar system to the inner planets. These bombardment episodes could influence atmospheric chemistry, ocean composition, and potentially the development of life on affected worlds. The recognition that stellar encounters shape planetary system evolution over time has implications for understanding exoplanets discovered around other stars. Many of these distant worlds exhibit orbital characteristics that differ dramatically from the relatively orderly arrangement of planets in our solar system. Interactions with passing stars may explain some of these unusual configurations, particularly in dense stellar environments where close encounters occur more frequently. As our understanding of galactic dynamics improves, we gain deeper appreciation for the complex environmental factors that influence planetary system development. The formation and evolution of worlds like Earth depend not only on local processes within individual stellar systems, but also on the broader galactic context in which these systems exist. The ongoing motion of stars through the galaxy ensures that stellar encounters will continue shaping our solar system's evolution far into the future. Each approaching star carries the potential to redistribute comets, alter asteroid orbits, or even capture or eject planetary objects. These interactions connect our local cosmic environment to the galaxy-wide processes of stellar formation, evolution, and death. The study of wandering suns ultimately reveals the dynamic, interconnected nature of our cosmic neighborhood. What appears from human timescales to be a stable arrangement of planets orbiting a solitary star actually represents a snapshot of an ever-changing gravitational dance involving hundreds of nearby stellar systems. Our solar system participates in this galactic choreography, occasionally experiencing close encounters that reshape its architecture and remind us of our place within the larger community of stars. The approaching encounter with Gliese 710 offers a remarkable opportunity for future astronomers to observe stellar flyby effects in real time. Unlike the ancient passage of Schultz's star, which can only be studied through its lingering gravitational signatures, the Gliese 710 encounter will unfold over timescales that allow direct observation of cause and effect relationships between stellar approaches and solar system dynamics. These stellar visitors serve as natural laboratories for testing our understanding of gravitational interactions on astronomical scales. Each close encounter provides unique opportunities to study how passing stars influence planetary system architecture, comet dynamics, and the long-term stability of orbital configurations established during the early stages of system formation. The cosmic perspective revealed by stellar encounter research demonstrates that Earth exists within a dynamic galactic environment where periodic gravitational disturbances represent natural features of planetary system evolution. The same processes that delivered water and organic compounds to the early Earth through comet bombardment continue operating today, connecting our world to the ongoing cycles of stellar birth, motion, and death that characterize our galaxy. As we continue mapping the motions of nearby stars and predicting future encounters, we develop increasingly sophisticated understanding of the forces that have shaped our solar system throughout its history. Each stellar flyby tells part of the story of how gravitational interactions between wandering suns create the complex, ever changing architecture of planetary systems throughout the galaxy. The recognition that our solar system regularly experiences close encounters with passing stars fundamentally changes how we view our cosmic environment. Rather than existing in isolation, we participate in a dynamic network of gravitational relationships that connect us to stellar neighbors across distances of many light years. The wandering suns that occasionally visit our cosmic neighborhood remind us that astronomical systems, like terrestrial ecosystems, exist as part of larger, interconnected communities where individual components influence one another across vast scales of space and time. In 2022, astronomers analyzing data from the European Space Agency's Gaia satellite noticed something peculiar in the motion of a star located 1,560 light years from Earth. The star appeared to wobble slightly as it moved across the sky, following a path that suggested it was orbiting around an unseen companion. Additional observations revealed that this companion possessed 9 times the mass of our Sun, yet emitted no detectable light whatsoever. The researchers had discovered Gaia BH1, the closest known black hole to our planet. This finding marked the beginning of a new era in black hole astronomy, one focused not on the bright active objects that announce their presence through dramatic displays of high energy radiation, but on the silent majority of black holes that drift through space like invisible predators. These dormant objects betray their existence only through the subtle gravitational tugs they exert on nearby stars, creating minute changes in stellar motion that require the most sophisticated instruments to detect. Within months of the initial discovery, the same team identified a second dormant black hole. Gaia BH2 lies 3,800 light years away in the constellation Centaurus, where it orbits with a red giant companion every 3.5 years. Like its closer cousin, this black hole contains approximately 9 solar masses compressed into a region smaller than most cities, creating a gravitational field so intense that not even light can escape its influence. The discovery of these nearby black holes challenged long held assumptions about how such objects should behave. Traditional models suggested that black holes in binary systems would steadily accrete material from their companion stars, heating the infalling matter to millions of degrees and creating brilliant X-ray sources visible across vast distances. Yet Gaia BH1 and BH2 remain completely dark, separated from their companions by distances too great for significant mass transfer to occur. The European Space Agency's Gaia mission represents humanity's most ambitious attempt to map the three-dimensional structure and motion of our galaxy. Positioned at a gravitationally stable point between Earth and the Sun, the space-based observatory continuously monitors more than 1 billion stars, measuring their positions with precision equivalent to observing a coin on the moon from Earth. These exquisite measurements reveal not only where stars are located, but also how they move through space over time. The detection of invisible companions requires patient analysis of stellar motion over multiple years. When a star orbits an unseen black hole, its path through space traces a subtle figure-8 pattern as viewed from Earth. The gravitational center of the system, called the barycenter, lies between the visible star and its dark companion. As both objects orbit this common center of mass, the star appears to wobble back and forth against the background of more distant stars. Identifying these astrometric signatures demands extraordinary precision because the wobbling motions are incredibly small. The companion stars of Gaia BH 1 and BH2 shift their apparent positions by amounts measured in milliseconds when at Tecton's angular distances, so tiny that they represent less than the width of a human hair, viewed from several kilometers away. Only Gaia's unprecedented positional accuracy makes such detections possible. The discovery process extends far beyond initial detection. Once astronomers identify a star exhibiting suspicious wobbling behavior, ground-based telescopes must conduct follow-up observations to confirm the nature of the invisible companion. These studies measure the radial velocity of the visible star, how fast it moves toward or away from Earth as it orbits the unseen object. Combined with Gaia's astrometric data, these measurements reveal the companion's mass and orbital characteristics. The confirmation process proved particularly challenging for the Gaia black holes because their wide orbital separations create subtle effects that unfold over timescales of years rather than days or months. Gaia BH1's companion star takes approximately 6 months to complete one orbit, while Gaia BH2's red giant requires more than 3 years. Detecting these long-period motions requires sustained observation campaigns that push both space-based and ground-based astronomy to their limits. In 2023, the Gaia team announced their most remarkable discovery yet. Buried within unreleased data from the spacecraft, astronomer Pasquale Panuzzo identified what initially appeared to be a measurement error. A star in the constellation Aquila showed such dramatic orbital motion that it seemed impossible. Further analysis revealed that this star orbits a black hole containing 33 times the mass of our Sun, the most massive stellar origin black hole ever found in our galaxy. Gaia BH3, as this monster became known, shatters previous records for stellar mass black holes in the Milky Way. Most such objects contain between 5 and 15 solar masses, making them compact but relatively modest by cosmic standards. The previous record holder, Cygnus X1, weighs approximately 21 times the Sun's mass. Gaia BH3's 33 solar masses place it in a category previously known only through gravitational wave detections from distant galaxies. The discovery of such a massive black hole so close to Earth, only 1926 light-years away, raises intriguing questions about stellar evolution and black hole formation. Current models struggle to explain how stars can produce such massive black holes without losing significant amounts of material during their final collapse. The existence of Gaia BH3 suggests that stellar death can sometimes proceed through pathways not fully understood by contemporary astrophysics. The detection of these dormant black holes represents only the beginning of what may prove to be a revolution in our understanding of the galactic black hole population. Theoretical calculations suggest that our galaxy contains millions of stellar mass black holes, yet fewer than 24 were known before Gaia began its systematic survey. The vast majority remain invisible, detectable only through their gravitational effects on nearby stars. The challenge of black hole detection becomes even more complex when considering objects that lack stellar companions entirely. Single black holes drifting through interstellar space leave no obvious signatures of their presence. They absorb light rather than emitting it, and their gravitational effects remain undetectable unless another object passes close enough to be influenced. These solitary wanderers could lurk anywhere in our cosmic neighborhood without revealing themselves to current detection methods. Recent theoretical work has explored the possibility that rogue black holes occasionally pass through established planetary systems like our own. Computer simulations suggest that close encounters with stellar mass black holes could dramatically reshape the architecture of the outer solar system, ejecting comets from the Oort cloud or even capturing entire planets into new orbits around the intruding object. The likelihood of such encounters remains extremely small on human timescales. Statistical analyses indicate that black holes capable of significantly disrupting planetary orbits approach within 100 astronomical units of the Sun, perhaps once every 100 billion years. While this represents an infinitesimally small probability, it illustrates the dynamic nature of our galactic environment and the exotic possibilities that exist within the realm of gravitational interactions. Supermassive black holes containing millions or billions of solar masses present different detection challenges and threat scenarios. These giants normally reside at the centers of galaxies, where they regulate star formation and influence galactic evolution through their immense gravitational fields. However, recent discoveries have revealed that some supermassive black holes have been ejected from their host galaxies entirely, becoming nomadic wanderers traveling between galactic clusters. The first confirmed detection of a wandering supermassive black hole came through observations of a tidal disruption event designated AT 2024 TVD. Located 600 million light years from Earth, this event occurred when a star approached too close to a 1 million solar mass black hole and was torn apart by tidal forces. Remarkably, this black hole lies 2,600 light years away from the center of its host galaxy, making it the first offset tidal disruption event ever observed. The discovery of wandering supermassive black holes opens new questions about the long-term stability of galactic structures. These objects, kicked out of their home galaxies through gravitational interactions with other supermassive black holes, or through asymmetric gravitational wave emission during merger events, carry enough mass to influence the evolution of any galaxy they encounter during their cosmic journeys. The detection of black holes through gravitational wave astronomy has added another dimension to our understanding of these invisible objects. The LIGO Virgo Cagra collaboration has identified hundreds of black hole mergers throughout the observable universe, revealing a population of massive black holes that had remained hidden from traditional astronomical surveys. These detections demonstrate that black holes routinely interact with one another across cosmic time, sometimes producing offspring more massive than either parent. The recent detection of gravitational wave event GW250114 represents the clearest signal ever recorded from a black hole merger. This event, detected in January 2025, provided the first confirmation of Stephen Hawking's black hole area theorem through direct observation. The merger involved two black holes with a combined mass of approximately 70 solar masses, producing gravitational waves that compressed and stretched space-time by amounts smaller than 1,000th the width of a proton. Advanced detection techniques continue expanding our ability to identify black holes across the galaxy. Future space missions will extend Gaia's capabilities by measuring stellar positions and motions with even greater precision over longer time baselines. These improvements will enable the detection of black holes with longer orbital periods and smaller gravitational effects, potentially revealing thousands of additional objects currently hidden within our cosmic neighborhood. Ground-based gravitational wave detectors are undergoing continuous improvements in sensitivity and detection range. Third-generation instruments currently under development will be capable of detecting black hole mergers throughout most of the observable universe, providing unprecedented insights into the formation and evolution of these exotic objects. The combination of electromagnetic and gravitational wave observations promises to reveal the complete life cycle of black holes from formation to final merger. The study of black holes has also revealed fascinating connections between these objects and fundamental physics. The extreme gravitational fields near black hole event horizons create conditions where general relativity's predictions can be tested with extraordinary precision. The confirmation of Hawking's area theorem through gravitational wave observations represents just one example of how black hole astronomy contributes to our understanding of space-time and gravity. Recent theoretical work has explored the possibility that our universe contains primordial black holes formed during the first moments after the Big Bang. These objects, if they exist, could have masses ranging from microscopic to stellar scales, potentially comprising some of the mysterious dark matter that influences galactic structure. The detection of primordial black holes would revolutionize our understanding of both cosmology and particle physics. The search for intermediate mass black holes, containing between 100 and 100,000 solar masses, represents another frontier in black hole astronomy. These objects, if they exist, would fill the gap between stellar mass and supermassive black holes, potentially providing clues about how the first supermassive black holes formed in the early universe. Several candidates have been identified in globular clusters and dwarf galaxies, but their nature remains controversial. Future missions may employ novel detection strategies to identify black holes that remain invisible to current methods. Proposals include monitoring stellar streams for signs of gravitational perturbation, searching for characteristic signatures of black hole evaporation, and using precision timing of pulsar signals to detect passing gravitational waves from distant black hole populations. The possibility of detecting black holes through their effects on interstellar dust and gas offers another promising avenue for discovery. When a black hole passes through a molecular cloud, its gravity can trigger star formation or create distinctive patterns in the distribution of cosmic material. These indirect signatures could reveal the presence of objects that would otherwise remain completely undetectable. As our galaxy continues its 200 million year journey around the galactic center, it encounters new stellar neighborhoods and gravitational environments. Each passage through spiral arms or close approaches to other galaxies creates opportunities for black holes to be scattered into new orbits or ejected entirely from their original locations. The dynamic nature of galactic evolution ensures that black hole populations continue changing over cosmic time. The recognition that black holes exist as both individual objects and members of complex gravitational systems has profound implications for understanding cosmic evolution. These invisible titans shape the formation of stars, regulate the growth of galaxies, and influence the large scale structure of the universe through their gravitational effects. Their presence connects processes occurring on scales from kilometers to billions of light years. Contemporary black hole research benefits from unprecedented international collaboration among astronomers, theorists, and engineers. The gravitational wave detection networks, space based astrometry missions, and ground based follow up observations represent coordinated efforts involving thousands of scientists from dozens of countries. This collaborative approach reflects the global nature of the challenge posed by these invisible and elusive objects. The philosophical implications of black hole research extend beyond astrophysics into fundamental questions about the nature of space, time, and information. Black holes represent regions where our current understanding of physics approaches its limits, creating natural laboratories for testing theories that cannot be explored through terrestrial experiments. Each new detection adds pieces to the cosmic puzzle of how gravity shapes the universe. The story of gravity wells in the dark ultimately illustrates humanity's growing ability to perceive the invisible architecture of the cosmos. Through patient observation, ingenious analysis techniques, and international cooperation, astronomers have begun mapping a hidden population of objects that profoundly influence galactic structure and evolution. These discoveries remind us that much of the universe remains unseen, awaiting detection by future generations of increasingly sensitive instruments. The dormant black holes lurking in our cosmic neighborhood serve as silent witnesses to billions of years of stellar evolution and galactic dynamics. Their presence demonstrates that even the most extreme objects predicted by physics actually exist in nature, following the mathematical laws that govern gravity, space, and time. As we continue developing more sophisticated methods for detecting these invisible giants, we gain deeper appreciation for the hidden complexity that surrounds us in the seemingly empty darkness between stars. Each newly discovered black hole contributes to our understanding of how these objects form, evolve, and influence their cosmic environments. The quiet companions of Gaia BH1, BH2, and BH3 represent just the first members of what may prove to be a vast population of invisible objects waiting for discovery. Their detection marks the beginning of a new chapter in astronomy, one focused on mapping the unseen gravitational landscape that shapes our galaxy's past, present, and future. Consider the span of time from the construction of the Great Pyramid of Giza to the present day, approximately 4.5 millennia, that encompass the entirety of recorded human civilization. Now multiply this interval by 1 million, and you approach the duration of a single geological period during which Earth endured the most sustained bombardment in its history. 4 billion years ago, our planet existed as a target in a cosmic shooting gallery where the prizes were survival and the penalty for losing was planetary sterilization. This epoch, known to scientists as the Late Heavy Bombardment, stretched across what may have been 200 million years of relentless impacts. During this extended trial, projectiles ranging from building-sized rocks to mountain-sized asteroids struck Earth and its celestial neighbors with frequencies that dwarf anything in more recent geological experience. The Moon, Mars, Mercury, and Venus all bear the permanent scars of this ancient violence, their surfaces pocked with basins hundreds of kilometers across that formed when massive objects traveling at interplanetary velocities transformed solid rock into temporary seas of molten material. The evidence for this tumultuous period emerges primarily from the moon, where the absence of weathering and tectonic processes has preserved a detailed record of impacts spanning billions of years. When Apollo astronauts collected samples of lunar rock between 1969 and 1972, they brought back fragments of a library written in stone and impact glass. Radiometric dating of these specimens revealed a puzzling pattern that would reshape our understanding of early solar system dynamics. Analysis of impact melts from different lunar landing sites showed a striking convergence of ages around 3.9 billion years. These rocks, formed when enormous collisions melted and reformed the lunar crust, seem to cluster within a relatively narrow window of geological time. The pattern appeared too organized to represent random chance, suggesting instead that the moon had experienced an episode of enhanced bombardment during this specific interval. The Apollo samples came from only a small fraction of the lunar surface, concentrated near three prominent impact basins: Mare Imbrium, Mare Nectaris, and Mare Serenitatis. Scientists initially worried that this limited sampling might skew their understanding of lunar impact history. However, subsequent studies of lunar meteorites that naturally fell to Earth confirmed similar age patterns. These specimens, representing material from across the moon's surface, including regions never visited by astronauts, showed the same clustering of impact ages around 3.9 billion years ago. The mechanism responsible for triggering this bombardment likely involved the migration of giant planets through the early solar system. According to the Grand Tack hypothesis, Jupiter formed approximately 3.5 times farther from the Sun than Earth currently orbits, then began migrating inward due to interactions with the disk of gas and dust still surrounding the young solar system. This migration carried Jupiter to within 1.5 astronomical units of the Sun, roughly the current orbital distance of Mars. Saturn's subsequent migration toward the Sun eventually brought it into gravitational resonance with Jupiter, fundamentally altering the dynamics of both planets. The resonance coupling reversed their migration direction, sending both giants back toward the outer solar system. This planetary choreography profoundly disrupted the orbits of countless smaller objects throughout the solar system, scattering asteroids and comets into chaotic trajectories that intersected the paths of the inner planets. The Grand Tack scenario elegantly explains several puzzling features of our solar system's architecture. Mars appears smaller than theoretical models predict for a planet forming at its distance from the Sun. If Jupiter spent time parked in the inner solar system during Mars's formation period, it would have scattered much of the raw material that Mars otherwise could have incorporated. This gravitational interference left the red planet with limited building blocks, explaining its modest size compared to Earth and Venus. The asteroid belt also bears signatures of Jupiter's ancient wandering. Modern asteroids exhibit a mixture of compositions that suggest origins from both the inner and outer solar system. Rocky objects typical of inner system formation orbit alongside primitive volatile rich bodies that formed in the cold outer reaches beyond the ice line. This compositional diversity reflects Jupiter's double passage through the asteroid belt, first scattering objects outward during its inward migration, then capturing some of them in stable orbits during its return journey. The bombardment triggered by these planetary migrations delivered far more than destruction to the early inner planets. Computer models suggest that the impactors carried substantial quantities of water and organic compounds, materials essential for the eventual emergence of life. Analysis of the impact rate during the late heavy bombardment indicates that Earth may have received the equivalent of several modern oceans worth of water during this period. Mars provides particularly compelling evidence for water delivery during the bombardment. Recent studies analyzing the chemical composition expected from impacting asteroids conclude that Mars could have received enough water to create a global ocean 300 meters deep. This calculation assumes all the delivered water remained liquid on the surface rather than being incorporated into the planetary interior or frozen at the poles. Such an ocean would have created dramatically different environmental conditions on early Mars, potentially supporting the complex chemistry necessary for life. The organic compounds delivered alongside water would have provided ready-made building blocks for prebiotic chemistry. Carbonaceous asteroids, rich in complex organic molecules formed in the cold outer solar system, contributed substantial quantities of amino acids, nucleotide bases, and other biomolecules to the early Earth. These materials supplemented whatever organic synthesis was occurring through terrestrial processes, creating a richer chemical environment for the origin of life. Paradoxically, the same impacts that delivered life's ingredients also pose severe threats to any emerging biological systems. The largest impacts during the bombardment released enough energy to vaporize significant portions of Earth's oceans, creating global steam atmospheres that persisted for thousands of years. Under such conditions, any surface life would face extinction, while even deep subsurface organisms might struggle to survive the extreme temperatures and pressures generated by major collisions. Some researchers have proposed that life could have survived these sterilizing events through impact-induced panspermia, the ejection of life-bearing rocks into space during large impacts. Mathematical models suggest that material blasted from Earth's surface could spend thousands of years in interplanetary space before returning to reseed the planet after conditions became more hospitable. This mechanism would allow life to literally escape extinction by temporarily leaving the planet, then return when the post-impact environment stabilized. The craters formed during the bombardment may have provided particularly favorable environments for early life. Large impacts create extensive hydrothermal systems that can persist for hundreds of thousands of years after the initial collision. These heated underground water systems offer stable temperatures, chemical energy sources, and protection from surface radiation conditions that many scientists consider ideal for the origin and early evolution of life. Impact-generated hydrothermal systems would have been especially important during the Hadean Eon, when Earth lacked the extensive deep ocean hydrothermal fields associated with modern plate tectonics. The fracturing and heating of rocks during major impacts creates geochemical conditions favorable for the synthesis of complex organic molecules from simple precursors. Laboratory studies demonstrate that hydrothermal conditions can drive the formation of amino acids, nucleotides, and even simple proteins from basic chemical building blocks. The timing of the late heavy bombardment coincides intriguingly with the earliest evidence for life on Earth. While the bombardment was winding down around 3.8 billion years ago, the first definitive biological signatures appear in rocks dating to approximately 3.5 billion years ago. This temporal correlation suggests that life may have emerged during or shortly after the bombardment period, possibly taking advantage of the chemical and environmental conditions created by the intense impact activity. However, the relationship between bombardment and early life remains complex and somewhat controversial. Some scientists argue that the bombardment would have repeatedly sterilized Earth's surface, preventing the establishment of stable ecosystems until the impact rate declined. Others contend that the delivery of water and organic compounds, combined with the creation of hydrothermal refugia, actually facilitated life's emergence despite the apparent hostility of the surface environment. Recent re examinations of the lunar impact record have raised questions about whether the late heavy bombardment represents a discrete cataclysmic event or simply the tail end of a continuously declining impact rate since solar system formation. Some researchers argue that the apparent clustering of impact ages around 3.9 billion years results from statistical artifacts in the analysis of lunar samples rather than reflecting a genuine increase in bombardment intensity. The debate over the bombardment's nature and timing continues as new analytical techniques provide increasingly detailed insights into early solar system dynamics. Advanced mass spectrometry allows scientists to measure isotopic signatures in lunar samples with unprecedented precision, revealing subtle chemical clues about the origins and trajectories of ancient impactors. These studies help distinguish between objects originating from different regions of the solar system, providing insights into the mechanisms that delivered them to the inner planets. The study of ancient impact spherules in Earth's oldest rock formations offers another window into bombardment history. These tiny glass beads form when impact generated molten droplets cool rapidly during their ballistic flight through the atmosphere. Layers of spherules in sedimentary rocks record individual impact events, creating a terrestrial complement to the lunar crater record. Analysis of these spherules can reveal the size, composition, and frequency of impacts affecting early Earth. Contemporary asteroid surveys provide additional context for understanding ancient bombardment rates. By cataloging the orbits and physical properties of objects currently crossing Earth's path, astronomers can model how impact rates have changed over geological time. These studies suggest that the current impact flux represents only a tiny fraction of the bombardment Earth experienced during its first billion years. The recognition that early Earth endured such intense bombardment has profound implications for understanding the conditions that shaped our planet's habitability. The bombardment delivered not only water and organic compounds, but also substantial amounts of metallic elements that contributed to Earth's core formation and magnetic field development. The energy released by major impacts may have influenced atmospheric composition and circulation patterns for millions of years after each event. Mars offers a particularly valuable natural laboratory for studying bombardment effects because its smaller size and thinner atmosphere preserved impact features that would be erased on Earth by erosion and tectonics. The red planet's ancient highlands retain craters from the earliest bombardment periods, allowing scientists to compare impact chronology across different regions of the solar system. These comparisons help test models of how giant planet migration influenced bombardment patterns throughout the inner solar system. The late heavy bombardment also provides insights into the formation and early evolution of other planetary systems throughout the galaxy. Many young stars show evidence of dusty debris disks that may represent planetary systems undergoing their own periods of intense bombardment. Understanding how bombardment shaped our solar system helps astronomers interpret observations of these distant systems and assess the likelihood of habitable conditions developing around other stars. Future lunar missions will provide opportunities to test and refine our understanding of bombardment chronology. Sample return missions to the moon's far side could reveal whether the impact history differs significantly between the near and far hemispheres. Detailed analysis of rocks from the moon's oldest impact basins could help resolve debates about the timing and intensity of early bombardment episodes. The development of increasingly sophisticated computer models allows researchers to simulate the complex gravitational interactions that shaped early solar system dynamics. These simulations can test different scenarios for giant planet migration and predict their effects on small body populations. As computing power increases, these models incorporate ever more realistic physics, providing detailed predictions that can be compared with observational evidence from lunar samples and asteroid surveys. The story of the late heavy bombardment ultimately illustrates the dynamic, violent nature of planetary system formation. Rather than assembling peacefully through gradual accumulation, planetary systems emerge from chaotic processes involving planetary migration, gravitational scattering, and intense bombardment periods. The same processes that threaten developing biospheres also deliver essential materials and create environmental niches where life can gain its first foothold. The bombardment's legacy persists in the chemical composition of Earth's oceans and atmosphere, the structure of the asteroid belt, and the size distribution of terrestrial planets. Every molecule of water on Earth may have arrived during this ancient period of cosmic chaos, carried aboard asteroids and comets, deflected from their original orbits by the gravitational dance of migrating giant planets. As we contemplate this ancient lottery, where chance determined which worlds would receive the materials necessary for life, we gain perspective on the contingent nature of habitability. Earth's current conditions result not from inevitable processes, but from a specific sequence of events involving planetary migration, orbital resonances, and impact delivery that might have unfolded differently under slightly altered circumstances. The cosmic lottery that was the late heavy bombardment reminds us that destructive and creative forces often work in partnership throughout the universe. The same impacts that repeatedly sterilized early Earth also delivered the water and organic compounds that made complex chemistry possible. The planets whose migration triggered this bombardment also helped establish the orbital architecture that provides long-term stability for Earth's climate and evolution. In studying this ancient period of violence and renewal, we encounter one of the fundamental themes governing planetary development: the transformation of chaos into order, destruction into creation, and cosmic violence into the delicate conditions that eventually permitted the emergence of life. The bombardment represents both the end of the solar system's chaotic youth and the beginning of the more stable conditions that would allow biology to take root and flourish on at least one world, orbiting an ordinary star in the galaxy's outer reaches. The deep time perspective, revealed through bombardment studies, places human existence within a broader context of geological processes operating over timescales that challenge comprehension. The 200 million years of intense bombardment lasted longer than the entire Mesozoic era, longer than the time since the supercontinent Pangaea broke apart. Yet this represents merely the final phase of Earth's formation, a brief, violent prelude to the billions of years of more gradual change that followed. Understanding the late heavy bombardment enhances our appreciation for the complex sequence of events that shaped our planet's habitability. Far from being a passive recipient of cosmic violence, early Earth emerged from this period transformed, enriched with the chemical ingredients for life, and sculpted by processes that created the environmental conditions necessary for biology to emerge and evolve. The cosmic lottery had delivered its prizes, setting the stage for the remarkable story of life that continues unfolding today on our bombardment scarred but ultimately triumphant world. What if the very fabric of reality exists in a state of delicate imbalance, poised precariously above an abyss where the familiar laws of physics cease to apply? Throughout our exploration of cosmic threats, we have encountered objects and events that challenge planets, disrupt atmospheres, and rearrange solar systems. Yet none of these phenomena touch the fundamental architecture of existence itself, the quantum fields that define how particles behave and how forces operate throughout the universe. In the deepest foundations of particle physics lies a possibility that dwarfs every other threat we have considered. Our universe may inhabit what physicists call a false vacuum, a condition where the fundamental energy state appears stable but actually rests atop a deeper, more stable configuration. Should this delicate balance ever collapse, the resulting transformation would propagate through space at the speed of light, rewriting the basic laws of nature and rendering chemistry, atomic structure, and perhaps even consciousness impossible. This scenario, known as false vacuum decay, represents the ultimate expression of scientific uncertainty about the stability of existence itself. Unlike asteroid impacts or stellar explosions, which threaten specific worlds or regions of space, vacuum decay would fundamentally alter the properties of space and time throughout the affected region. The process would be swift, inexorable, and absolutely undetectable until the moment it arrived. The theoretical foundation for this possibility emerges from quantum field theory, the mathematical framework that describes how particles and forces interact at the most fundamental level. Every particle we observe, meus electrons, quarks, photons, represents excitations in underlying quantum fields that pervade all of space. These fields exist in what physicists term vacuum states, configurations that define the baseline energy and properties of empty space itself. The discovery of the Higgs boson at the Large Hadron Collider in 2012 provided experimental confirmation of the Higgs field, a quantum field responsible for giving other particles their mass. The measured mass of this particle approximately 125 billion electron volts Lyra, represents a crucial parameter in determining whether our universe occupies a stable or metastable vacuum state. Precision calculations using the most accurate available measurements indicate that our vacuum may indeed be metastable rather than absolutely stable. The mathematical analysis depends critically on the masses of the Higgs boson and the top quark, along with the strength of the strong nuclear force. Current measurements place these parameters tantalizingly close to the boundary between stability and metastability, creating what physicists describe as a near critical condition. The metastability arises from complex interactions between different quantum fields. The Higgs field creates a potential energy landscape resembling a Mexican hat, with the field's current value corresponding to the circular rim around the hat's edge. This configuration appears stable because any small perturbation would cause the field to return to its current state. However, quantum mechanics permits tunneling effects that could occasionally kick the field into a much deeper energy minimum at the hat's center. Such a transition would begin with the spontaneous formation of a microscopic bubble where the Higgs field assumes its true vacuum value. Initially smaller than atomic nuclei, this bubble would possess lower energy density than the surrounding false vacuum. The interface between true and false vacuum would provide the surface tension needed to maintain the bubble's integrity while allowing rapid expansion. The expansion would proceed at nearly the speed of light, limited only by the curvature of space-time itself. As the bubble grows, its wall would convert surrounding false vacuum into true vacuum, transforming the fundamental properties of space within its ever-expanding boundary. The process would be irreversible and impossible to halt once initiated, representing a permanent phase transition in the structure of reality. Inside the expanding bubble, the altered Higgs field value would modify the masses of all fundamental particles. Electrons might become thousands of times heavier, while quarks could lose their binding properties entirely. The fine structure constant that governs electromagnetic interactions might shift dramatically, preventing atoms from maintaining stable electron orbitals. Even the strength of nuclear forces could change, destabilizing atomic nuclei and rendering matter as we understand it impossible. The implications extend far beyond particle physics into the realm of existence itself. Chemistry depends on specific ratios between particle masses and force strengths that allow atoms to form stable configurations. Complex molecules require precise electromagnetic interactions between electrons and nuclei. Life as we know it emerges from intricate chemical processes that would cease to function if fundamental constants shifted beyond narrow ranges. Recent experimental work has brought this abstract theoretical possibility into the laboratory for the first time. Teams at European universities have created ultra-cold atomic systems that exhibit false vacuum decay through bubble formation. Using gases of sodium atoms cooled to within millionths of a degree above absolute zero, researchers observed the spontaneous nucleation and growth of bubbles, representing transitions from metastable to stable states. These experiments employ ferromagnetic superfluids as analogs for the quantum fields governing fundamental particle interactions. While the specific physics differs dramatically from cosmic false vacuum decay, the underlying mathematical structures remain remarkably similar. The laboratory observations confirm theoretical predictions about bubble formation rates, expansion dynamics, and the role of thermal activation in triggering decay processes. The experimental evidence demonstrates that metastable systems do indeed undergo spontaneous decay through bubble nucleation when conditions permit. The measured bubble formation rates scale exponentially with experimental parameters related to energy barrier properties, precisely matching theoretical expectations. These results provide the first direct empirical support for the fundamental mechanisms that would govern cosmic vacuum decay. The timescales involved in potential cosmic vacuum decay stretch far beyond human comprehension. Current calculations suggest that if our vacuum is metastable, its average lifetime exceeds 10 to the 65th power years. This interval dwarfs the current age of the universe by more than 50 orders of magnitude, placing any potential decay in the unimaginably distant future under normal circumstances. However, extraordinary events might potentially trigger premature vacuum decay. Some theoretical scenarios propose that extremely high energy particle collisions, such as those occurring near black holes or during the early universe's most violent epochs, could provide sufficient energy to nucleate vacuum bubbles. The formation of primordial black holes, cosmic string interactions, or phase transitions during cosmic inflation represent potential triggering mechanisms. The search for signatures of vacuum instability continues through multiple experimental approaches. Precision measurements of particle masses and coupling constants at the Large Hadron Collider provide increasingly stringent constraints on the stability landscape. Future colliders with higher energies and greater precision may definitively determine whether our vacuum occupies a stable or metastable configuration. Cosmological observations offer another window into vacuum stability. The cosmic microwave background radiation carries information about conditions during the universe's first moments, when vacuum fluctuations were most likely to trigger any decay processes. The absence of signatures indicating past vacuum transitions provides additional evidence for stability over cosmic timescales. The philosophical implications of false vacuum decay touch the deepest questions about the nature of existence and reality. Unlike other cosmic threats that threaten specific structures or processes, vacuum decay would eliminate the fundamental conditions that make structure formation possible. The transition would not destroy existing matter so much as transform the underlying rules governing how matter can exist. The possibility that our universe's apparent stability rests on quantum mechanical foundations introduces profound uncertainty into our understanding of reality's permanence. The familiar world of atoms, molecules, and electromagnetic forces might represent only one possible configuration among many maintained by quantum field dynamics that we are only beginning to comprehend. Contemporary research into vacuum stability benefits from interdisciplinary collaboration between particle physicists, cosmologists, and condensed matter theorists. The mathematical tools developed for understanding high-energy particle interactions find applications in laboratory systems exhibiting analogous phase transitions. This cross-pollination of ideas accelerates progress in understanding metastability across vastly different energy scales. The development of quantum field theory over the past century has revealed that what appears solid and permanent often emerges from underlying quantum fluctuations in field dynamics. The vacuum of space, rather than being empty nothingness, teams with virtual particle creation and annihilation. These processes contribute to measurable effects, like the Casimir force and vacuum polarization, demonstrating the active nature of apparently empty space. False vacuum decay represents the ultimate expression of this quantum activity, where fluctuations in field values could potentially restructure reality itself. The mathematical formalism describing this process employs the same theoretical tools used to understand radioactive decay, chemical reaction rates, and phase transitions in materials science, highlighting the universal nature of probability and metastability. The detection challenges posed by vacuum decay differ fundamentally from those associated with other cosmic threats. Asteroid impacts, gamma ray bursts, and stellar explosions announce their presence through electromagnetic radiation, gravitational waves, or particle emissions detectable across vast distances. Vacuum decay provides no such warning signals because the expanding bubble travels at light speed, arriving simultaneously with any information about its existence. This property makes vacuum decay unique among cosmic catastrophe scenarios in its absolute unpredictability and inevitability. Once nucleated, the decay would proceed inexorably, immune to any conceivable intervention or deflection strategies. The affected region would experience instantaneous transformation of physical laws, creating conditions utterly incompatible with any form of matter or energy organization based on current physics. The study of vacuum metastability has also shed light on the early universe's evolution and the formation of fundamental particles. The Higgs field underwent its own phase transition shortly after the Big Bang, settling into its current vacuum state and establishing the mass patterns we observe today. Understanding the dynamics of such transitions helps cosmologists model the universe's first moments and the processes that determined its subsequent evolution. Future theoretical developments may modify our understanding of vacuum stability through discoveries of new particles or forces beyond the standard model. Supersymmetric extensions of current theory, extra-dimensional models, or quantum gravity effects could stabilize the vacuum or reveal additional metastable states. The landscape of possible vacuum configurations might prove far richer and more complex than current models suggest. The emergence of quantum computing and advanced simulation techniques provides new tools for exploring vacuum stability and false vacuum decay processes. These computational approaches allow researchers to model systems with many interacting quantum fields, potentially revealing stability mechanisms or decay pathways not accessible through analytical calculations alone. Laboratory studies of vacuum decay analogs continue expanding beyond ultra-cold atomic systems to include quantum materials, superconducting circuits, and other condensed matter platforms. Each system offers unique advantages for probing different aspects of metastability and phase transition dynamics. The accumulating experimental evidence helps validate theoretical models while revealing unexpected phenomena that enrich our understanding of quantum field behavior. The international scientific community has embraced vacuum stability research as a fundamental challenge requiring unprecedented precision in both experimental measurements and theoretical calculations. Collaborative efforts involving particle accelerator facilities, astronomical observations, and condensed matter laboratories work together to constrain the parameters governing our universe's ultimate fate. Educational initiatives have begun incorporating vacuum stability concepts into undergraduate and graduate curricula, recognizing that future physicists will need to understand quantum field dynamics to address emerging questions in fundamental physics. These programs emphasize the interconnections between particle physics, cosmology, and condensed matter research that characterize modern approaches to vacuum stability studies. The concept of vacuum decay has also influenced philosophical discussions about the nature of scientific knowledge and the limits of predictability in physical systems. The possibility that reality itself rests on quantum mechanical foundations challenges traditional notions of permanence and stability, suggesting that existence might be more contingent and probabilistic than classical physics implied. As we contemplate the possibility that our universe inhabits a false vacuum balanced above deeper energy states, we encounter perhaps the most profound uncertainty in all of science. Unlike other cosmic threats that emerge from identifiable objects or processes, vacuum decay would arise from the quantum mechanical properties of space itself, transforming the fundamental conditions that define what it means for anything to exist. The timescales involved place any potential decay far beyond human concern, yet the mere possibility illuminates the remarkable contingency underlying apparent stability. Every atom, every molecule, every physical process depends on precise relationships between fundamental constants that quantum field theory suggests might not be permanent features of nature. In this ultimate catastrophe scenario, destruction would not arrive through collision, explosion, or gravitational disruption, but through the quiet restructuring of physical law itself. The expanding bubble of true vacuum would propagate through space like a cosmic revelation, rewriting the rules of existence and demonstrating that even the most fundamental aspects of reality remain subject to change. The study of false vacuum decay ultimately returns us to the deepest questions about the universe's nature and our place within it. Are the physical laws we observe universal and permanent, or do they represent temporary configurations in an ever evolving cosmic landscape? Does our existence depend on the continued stability of quantum fields we barely understand? These questions push the boundaries of human knowledge toward realms where physics and philosophy converge. The possibility of vacuum decay reminds us that our scientific understanding, however sophisticated, rests on foundations that may themselves prove impermanent. In contemplating this ultimate catastrophe, we confront both the power and the limits of human comprehension in the face of cosmic mysteries. The wondrous nature of this investigation lies not in the threat it poses, remote beyond practical concern, but in what it reveals about the structure of reality. The universe emerges as far more strange and contingent than everyday experience suggests, sustained by quantum mechanical processes that admit possibilities beyond our imagination. Perhaps the most remarkable aspect of vacuum decay research is how it connects the smallest scales of quantum mechanics to the largest questions about cosmic evolution and the ultimate fate of everything that exists. In probing the stability of vacuum states, physicists explore the interface between the known and the unknowable, between the reliable patterns of natural law and the fundamental uncertainty that quantum mechanics reveals at the heart of all physical processes. The story of false vacuum decay ultimately celebrates the human capacity to contemplate possibilities that transcend immediate experience and practical concern. In asking whether reality itself might prove unstable, we demonstrate the remarkable reach of scientific inquiry and the profound questions it continues to pose about the nature of existence